We almost missed the largest star in the universe, Stephenson 218, 2,149 solar radii. A sphere so incomprehensibly massive that light itself would take 9 hours to cross from one side to the other. Buried deep inside a dust-choked stellar cluster 19,000 light-years from Earth, hidden in plain sight, nearly lost to history because no one thought to look hard enough at the right patch of sky, and for years we had the wrong champion. Scuti held the crown with measurements pushing 1,700 solar radii, textbooks updated, documentaries filmed. Comparison graphics shared millions of times across the internet. Then the data was rerun, the distance recalculated, the radius collapsed to 900, the king was dethroned, and most of the world didn't even notice. But Stephenson 218 is not a revision. It is not a mistake waiting to be corrected. It is a monster that makes our sun look like a grain of sand on an endless beach. If you placed it where our sun sits right now, its surface would swallow Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, and reach halfway to Saturn. One star, 10 billion times the volume of the thing that gives us every sunrise, and we very nearly never found it at all. So what turns an ordinary ball of fusing hydrogen into something so large it breaks your sense of scale? How does a star grow to a size that seems to violate the basic rules of what a star should be? And what does it mean that the universe can hide something this colossal in a place we've been looking at for decades? This is the story of 5 titans and the one we almost lost. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You walk outside on a clear morning. The sky is blue. The air smells like grass or coffee or exhaust, depending on where you live. And there, sitting in the sky like it has every single day of your life, is the sun. Familiar, predictable, unremarkable in the way that breathing is unremarkable. You've seen it so many times that your brain has filed it away under background noise, right next to the hum of your refrigerator and the feel of socks on your feet. And that familiarity, that deep, comfortable certainty that the sun is just there, has made it almost impossible for most people to grasp what they're actually looking at. The sun is not a lamp, it is not a light bulb hanging in the sky. It is a ball of plasma, held together by its own gravity, burning hydrogen into helium in a furnace so hot that the core reaches about 15 million degrees Celsius. That's 15 with 6 zeros after it. At that temperature, atoms don't behave the way they do on Earth. Electrons are stripped away, nuclei slam into each other hard enough to fuse. And every second, deep in the core of that glowing sphere you barely glance at on your way to work, about 600 billion kilograms of hydrogen are converted into helium. In the process, roughly 4 billion kilograms of matter vanish entirely, transformed into pure energy, according to Einstein's famous equation. 4 billion kilograms every second. That energy works its way outward through layers of roiling plasma, taking tens of thousands of years to fight its way from the core to the surface, and then it streams out into space as light. 8 minutes later, a tiny fraction of it lands on your face, and you call it a sunny day. The sun is about 1.39 million kilometers across. If you prefer miles, that's roughly 864,000. Either way, the number is large enough that it stops meaning much to a human brain. So let's try this instead. The Earth, the planet you're standing on right now, has a diameter of about 12,700 kilometers. Line up 109 Earths in a row, edge to edge, and that's how wide the sun is. 109. If the Sun were a hollow ball, you could fit about 1.3 million Earths inside it. Not 1,000, not 100,000. 1.3 million. If you started filling the Sun with Earths like a jar of marbles, you could keep going until you ran out of Earths, then go find more planets, fill those in too, and you'd still have room left over. And yet, standing here on the surface of this rock, the Sun looks small. It takes up about half a degree of the sky. You can cover it with your thumb held at arm's length. The Moon, which is a lifeless ball of rock about a quarter the size of Earth, looks exactly the same size in the sky. Same angular diameter, same apparent scale. That's not because the Sun and Moon are secretly the same size. It's because the Sun is sitting roughly 150 million kilometers away, far enough that its true size is compressed into a dot. That distance from Earth to the Sun is called an astronomical unit. Astronomers use it as a measuring stick for everything in the solar system. 1 AU, a number so common in space science that people forget how staggeringly large it actually is. Light, which travels at roughly 300,000 kilometers per second, takes 8 minutes and 20 seconds to cross that gap. If you could somehow build a highway to the Sun and drive at a steady 100 kilometers per hour without stopping to eat or sleep or refuel, the trip would take about 170 years. The Sun is not just big, it is overwhelmingly, violently massive. Mass and size are not the same thing, by the way. You can have a large object with low mass, like a balloon, or a small object with high mass, like a lead weight. The Sun has both. Its mass is about 2 times 10 to the power of 30 kilograms. In more human terms, that's about 333,000 times the mass of Earth. Take every mountain, every ocean, every continent, every car and building and human being and ant and grain of sand on this planet, add it all up, then multiply that total by 333,000. That's the Sun, and it's still not done. The Sun contains more than 99.8% of all the mass in the entire solar system. Jupiter, Saturn, Uranus, Neptune, all the other planets, all the moons, all the asteroids, all the comets, all the dust drifting between the orbits, every single object bound to our star, all of it together makes up less than 0.2% of the total. The Sun is not the center of the solar system because we decided to draw it that way on a chart. It is the center because its gravity is so dominant that everything else has no choice but to fall into orbit around it. That gravity is what holds you to the surface of Earth, not directly. Earth's gravity does that. But Earth orbits the Sun because the Sun's gravity reaches out across 150 million kilometers of empty space and pulls on this planet hard enough to keep it moving in a circle year after year. If the Sun vanished right now, not exploded, just disappeared, Earth would stop orbiting 8 minutes and 20 seconds later. The planet would fly off in a straight line into interstellar space like a stone released from a sling. We wouldn't notice the gravity disappearing immediately. We'd notice the light going out first. Then, 8 minutes later, the night would never end. The Sun formed about 4.6 billion years ago. The solar system did not exist before that. There was no Earth, no Jupiter, no rocky debris waiting to be swept up into planets. There was only a cloud. A vast, cold, slowly rotating cloud of gas and dust called a molecular cloud, made mostly of hydrogen and helium left over from the Big Bang, with a light dusting of heavier elements forged inside earlier generations of stars that had lived, died, and exploded long before our Sun was born. Something disturbed that cloud. Maybe a nearby supernova sent a shockwave rippling through the region. Maybe the cloud simply reached a critical density where its own gravity took over. Either way, it began to collapse. As it collapsed, it spun faster, the way a figure skater spins faster when they pull their arms in. The center of the cloud heated up. Gravity pulled more and more material inward. The pressure and temperature in the core climbed, and eventually, about 10 million degrees Celsius into the process, hydrogen nuclei started fusing into helium. The cloud lit up. A star was born. The rest of the cloud, the material that didn't fall into the sun, flattened into a spinning disk. Within that disk, tiny grains of dust stuck together. Grains became pebbles, pebbles became boulders, boulders became planetesimals, planetesimals became planets. The whole process took a few tens of millions of years, which sounds like a long time until you remember that the sun has been burning for 4.6 billion. The construction phase was a blink. Everything since then has been the sun doing what it was built to do, shine, and it shines because of fusion. At the core of the sun, temperatures sit around 15 million degrees Celsius. At that temperature, hydrogen nuclei, which are just single protons, are moving so fast that when they collide, they can overcome the electromagnetic force trying to push them apart. Normally, two protons repel each other. They're both positively charged, and like charges repel. But if you slam them together hard enough, at high enough speeds, they get close enough for the strong nuclear force to take over. That's the force that binds protons and neutrons together inside an atomic nucleus. It's stronger than electromagnetism, but it only works at extremely short ranges. Once two protons get past the electromagnetic barrier, the strong force locks them together. One of the protons converts into a neutron, releasing a positron and a neutrino in the process. What you're left with is a deuterium nucleus, one proton, one neutron. From there, the deuterium can fuse with another proton to form helium-3. Two protons, one neutron. Then two helium-3 nuclei can collide and fuse into helium-4, spitting out two protons in the process. Helium-4 is stable. It's the second lightest element in the universe, and it's what the sun has been making in its core for the last 4.5 billion years. Every time hydrogen fuses into helium, a tiny amount of mass disappears. It doesn't go anywhere. It converts into energy. That's what Einstein's equation tells you. Energy equals mass times the speed of light squared. The speed of light is a very large number. Square it, and it gets enormous. Which means even a small amount of mass, when converted into energy, produces an almost unimaginable amount of power. The sun converts about 4 million tons of matter into energy every second. 4 million tons, gone, turned into light and heat, and it has enough hydrogen in its core to keep doing that for another 5 billion years. That energy doesn't shoot straight out of the core. If it did, the sun's surface would be far hotter than it actually is. Instead, the energy produced by fusion gets trapped. Photons, particles of light, are born in the core and immediately slam into other particles. They scatter, get absorbed, re-emitted, absorbed again, scattered again. A photon, produced in the core of the sun, doesn't travel in a straight line to the surface. It ricochets through the interior like a pinball, bouncing trillions upon trillions of times. The trip from core to surface, a journey of less than 700,000 kilometers in a straight line, takes somewhere between 10,000 and 170,000 years, depending on whose model you trust. The photon that hit your face this morning was born when humans were still figuring out how to make fire. Once the photon finally reaches the surface, it's free. It streams out into space at the speed of light. 8 minutes later, it crosses the orbit of Earth. Some of those photons hit the atmosphere, scatter, and give you a blue sky. Some hit the ground, warm the soil, evaporate water, drive the weather. Some hit a leaf and get absorbed by chlorophyll, kicking off the chemical process that turns carbon dioxide and water into sugar and oxygen. Photosynthesis, the foundation of almost every food chain on the planet. Every time you eat, you are consuming energy that originated in the core of the sun. The apple, the chicken, the fish, the bread. All of it traces back to sunlight captured by plants or by algae in the ocean. You are built from sunlight. Your muscles run on sunlight. Your thoughts are powered by electrical signals in a brain fueled by glucose that came from sunlight. The sun is not just a light in the sky. It is the engine that runs Earth, and yet for all that power, the sun is ordinary. Astronomers classify it as a G-type main sequence star. The G refers to its color, which is technically white, though it looks yellow to us because of how our atmosphere scatters light. The main sequence part means the sun is in the long stable phase of its life, where it fuses hydrogen into helium in its core. Most stars spend the majority of their existence on the main sequence. It's not a location, it's a state, and the sun is right in the middle of that state. The V in its full classification, G2V, stands for dwarf, not because the sun is small, it's not, but because compared to the true giants of the galaxy, stars that have evolved off the main sequence and swollen to hundreds of times their original size, the sun is unremarkable, medium-sized, average. There are stars far smaller, dim red dwarfs that barely glow, sipping their hydrogen so slowly they'll outlive the sun by trillions of years. And there are stars far larger, blue supergiants burning so ferociously they'll exhaust their fuel in a few million years and detonate. The sun sits in between, stable, predictable, boring in the best possible way, which is lucky for us. If the sun were much smaller, Earth would freeze. If it were much larger, it would burn out before life had time to evolve. The sun's mass, its temperature, its position on the main sequence, all of it sits in a narrow range that allows a planet like Earth to orbit in what astronomers call the habitable zone. Not too hot, not too cold, liquid water on the surface, an atmosphere that doesn't boil away or freeze solid. The conditions that, as far as we know, are necessary for life. There is nothing special about the sun except that it happens to be the right kind of ordinary at exactly the right time, in exactly the right place. But here's the thing. Knowing all of that, understanding the numbers, reading the statistics, none of it actually makes the sun feel big. You can read that the sun contains 333,000 Earth masses, and your brain will process the sentence, file it away and move on. You won't feel it, because human brains are not built to handle cosmic scales. We evolved to understand the size of a predator, the distance to a water source, the height of a tree. Our sense of scale tops out somewhere around the size of a mountain. Beyond that, everything just becomes big. There's no difference emotionally between a million and a billion. Both are abstract. Both live in the same mental file labeled a lot. Try this. Imagine a sphere 1 meter across. You can picture that. It's about the size of a large beach ball. Now imagine a sphere 100 meters across. That's harder, but you can still do it. It's about the size of a small building. Now imagine a sphere 1 kilometer across. You're starting to lose the sense of it. A kilometer is a distance you can walk, but a sphere that size is harder to hold in your mind. Now try 100 kilometers, 1,000, 10,000. By the time you get to 700,000 kilometers, the number has stopped meaning anything. It's just a number. Your brain has given up trying to visualize it. And that's the problem with understanding the sun. You can stack metaphors. You can say it would take 109 Earths to span its diameter. You can say it contains more than 1 million Earths by volume. You can say it converts 4 million tons of matter into energy every second. And none of those comparisons will make you feel the size of it, because you have never seen 109 Earths. You have never held 1,000,000 Earths in your hand. You have never watched 4 million tons of matter vanish. The numbers are real, but they're too large to land. The best you can do is zoom out. Start with something small, an ant, then a human, then a building, then a mountain, then Earth, then the sun. Each step is a jump so large that the previous scale becomes meaningless. An ant standing on a human would see a landscape. A human standing on Earth sees a curved horizon. Earth, sitting next to the sun, is a dot, a single pixel in a photograph, and we're about to go much, much larger, because the sun, for all its mass, for all its power, for all the fact that it holds our entire solar system in its gravity and powers every living thing on this planet, is small, not by human standards, by stellar standards. There are stars out there, burning in distant corners of the galaxy, that make the sun look like a marble next to a hot air balloon. Stars so large that if you placed them where the sun is, their outer layers would swallow Earth, Venus, Mercury, and keep going. Stars that shouldn't exist according to the physics we thought we understood. Stars that sat in our telescopes for years before anyone realized what they were looking at. And the largest of them, the reigning champion, the single biggest star we've ever confirmed, is so massive that astronomers still argue about whether the measurement is even possible. Chapter 2. Unveiling the Titans, Cephei and Antares. So, the Sun is enormous by human standards and small by cosmic ones. That's the setup. Now we move on to the stars that make astronomers pause mid-sentence and recalculate their numbers to make sure they didn't drop a decimal point somewhere. The stars that forced the entire field to expand its mental category for what counts as large. The stars that, when you plot them on a scale diagram next to the sun, make the sun disappear. We're talking about red supergiants. And if you've never heard that term before, you're about to become very familiar with it, because almost every star on the list of cosmic monsters falls into this category. Red supergiants are not a separate species of star, they're a phase, a late-stage transformation that happens to certain massive stars after they've burned through the hydrogen in their cores and started fusing heavier elements. They are what happens when a star runs out of the fuel that kept it stable for millions of years and begins the long, dramatic slide toward death. Here's the short version of how it works. A star like the Sun fuses hydrogen into helium in its core. That process releases energy, and that energy creates an outward pressure that balances the inward crush of gravity. The star sits in equilibrium. Core pushes out. Gravity pushes in, and the two forces lock into a stalemate that can last for billions of years. Eventually, the hydrogen in the core runs out. The core contracts. As it contracts, it heats up. The outer layers of the star, which still contain plenty of hydrogen, start fusing in a shell around the now dormant helium core. That shell fusion dumps enormous amounts of energy into the star's outer envelope. The envelope expands. The surface area increases dramatically. The star's outer layers cool down because they're now much farther from the core, and cooler gas glows red instead of white or blue. The result is a red giant. For stars much more massive than the Sun, the process doesn't stop there. The core eventually gets hot enough to start fusing helium into carbon and oxygen. Then, if the star is heavy enough, it fuses carbon into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, silicon into iron. Each stage releases less energy than the one before it and burns faster. A massive star might spend millions of years fusing hydrogen, a few 100,000 years fusing helium, and only a few days fusing silicon. By the time the core is made of iron, the star has run out of options. Iron fusion doesn't release energy, it absorbs it. The core collapses in a fraction of a second. The outer layers slam inward, rebound off the collapsing core, and explode outward in a supernova. What's left behind is either a neutron star or a black hole, depending on how much mass was there to begin with. Red supergiants are stars caught in the middle of that process. They've exhausted their core hydrogen, they're fusing heavier elements in layers like an onion, and they've swollen to sizes that make the sun look like a grain of sand on a beach. They are rare, they are short-lived, and they are unimaginably huge. The first one we're going to talk about is Cephei. If you've never heard of it, don't feel bad, it's not exactly a household name. But among astronomers, especially those who care about stellar extremes, Cephei is legendary. It sits in the constellation Cepheus, a faint grouping of stars shaped vaguely like a house with a pointed roof, located near the North Celestial Pole. If you live in the Northern Hemisphere and you know where to look, you can see Cephei with your naked eye on a clear night. Not easily. It's a fourth magnitude star, which means it's dim enough that light pollution will wash it out. But if you're somewhere dark and you're patient, you can find it. The remarkable thing about Cephei is not that you can see it. The remarkable thing is what you're actually looking at when you do. That faint reddish dot, barely visible without a telescope, is one of the largest stars in the entire Milky Way galaxy. If you could lift Cephei out of its current position, about 6,000 light-years from Earth, and drop it into the center of our solar system where the Sun currently sits, the star's outer atmosphere would extend somewhere past the orbit of Mars. Some models push it even farther, out near Jupiter. One estimate puts the radius at about 1,500 times the radius of the Sun. Another says 1,260. The exact number depends on which study you trust and which method they used to calculate the size, but the range doesn't really matter. Whether it's 1,200 solar radii or 1,500, the result is the same. Cephei is so large that if Earth were still in its current orbit, it would be inside the star. Not near the star, not orbiting close to the star. Inside it. Fully submerged in the outer layers of the star's atmosphere, getting cooked by gas that, even at the star's relatively cool surface temperature of about 3,400 degrees Celsius, would vaporize anything made of rock or metal in seconds. There would be no collision, no violent impact. Just a quiet dissolving as Earth's atoms mixed into the thin outer envelope of a dying giant. That image by itself should be enough to make you pause. But let's go further. Let's talk about luminosity. Cephei is not just large, it is ferociously bright. The star pumps out about 100,000 times more visible light than the Sun. Some estimates go higher, closer to 200,000 if you account for the full range of radiation, not just the light your eyes can detect. The star's surface is cooler than the Sun's, which is why it glows red instead of white. But it has so much surface area that even at that lower temperature, it radiates an almost incomprehensible amount of energy into space. If you could somehow stand on a planet orbiting Cephei at the same distance Earth orbits the Sun, you wouldn't see a sun in the sky. You'd see a wall of glowing red that filled half the horizon. The heat would melt the surface. The light would outshine anything you've ever experienced by orders of magnitude. There would be no day and night, just one endless, crushing brightness. And here's the strangest part. Despite all of that, despite the size, despite the luminosity, Cephei is not even close to being the brightest object in the night sky. It sits at around magnitude 4, sometimes dimmer. It's barely visible. You can see it, but only just. The reason is distance. Mu Cephei is 6,000 light-years away. At that range, even a star pumping out 100,000 times the sun's luminosity looks like a dim ember. If Mu Cephei were as close to us as, say, Sirius, the brightest star in Earth's night sky, which sits only 8.5 light-years away, Mu Cephei would outshine everything. It would be visible during the day. It would cast shadows at night. It would dominate the sky so completely that human culture, human mythology, human religion would all have formed around it. But it's not close. It's thousands of light-years away, tucked into an obscure corner of a dim constellation most people have never heard of. And so it sits there, quietly, one of the largest objects in the galaxy, and almost nobody notices. William Herschel noticed. Herschel was a German-born British astronomer best known for discovering Uranus in 1781, the first planet found in recorded history that wasn't known to the ancients. He was also an obsessive observer who spent decades cataloguing stars, nebulae, and anything else his telescopes could resolve. In 1840-something, sources differ slightly on the exact year, Herschel pointed his telescope at Mu Cephei and was struck by its color. Most stars look white or pale blue through a telescope. Mu Cephei looked deep red, almost orange. The kind of red you see in a dying coal or a glass of dark wine held up to candlelight. Herschel described it as a Garnet Star, and the name stuck. To this day, Mu Cephei is often called Herschel's Garnet Star, a nickname that manages to sound both poetic and slightly pretentious at the same time. The color isn't decorative, it's diagnostic. Red stars are cool stars, at least by stellar standards. Mu Cephei's surface sits at around 3,400 Kelvin. For comparison, the Sun's surface is about 5,700 Kelvin. That difference matters because a star's color tells you its temperature, and its temperature tells you what stage of life it's in. Blue stars are young, hot, and burning fuel at a ferocious rate. Yellow stars, like the Sun, are middle-aged and stable. Red stars are either very small and dim, like red dwarfs, or very large and dying, like red giants and red supergiants. Mu Cephei is firmly in the latter category. It is not a young star. It is not a stable star. It is a star in its final act, burning through the last reserves of fuel in its core before it runs out of options and detonates. Mu Cephei is also a variable star. Its brightness changes over time, not wildly, not in a way that would be obvious to the naked eye from night to night, but measurably. The star's magnitude ranges from about 3.4 at its brightest to 5.1 at its dimmest. That's a difference of more than a full magnitude, which translates to a change in brightness of about a factor of 4. The variations are irregular. Sometimes the star dims slowly over months. Sometimes it rebounds quickly. The pattern doesn't repeat with perfect regularity, which is why astronomers classify it as a semi-regular variable rather than a predictable pulsating star like a Cepheid. The variability is caused by instability in the star's outer layers. Mu Cephei is so large and so diffuse that its outer atmosphere is barely held together by gravity. Gas swells outward, cools, falls back, heats up, and swells again in a slow, chaotic rhythm. The star is essentially breathing. Each breath takes weeks or months, and with each cycle, the amount of light reaching Earth shifts slightly. The variability was first noticed by John Russell Hind in 1848. Hind was a British astronomer who spent years cataloguing variable stars, and Mu Cephei was one of his finds. Since then, the star has been monitored almost continuously. Its light curve, the graph of its brightness over time, is one of the longest continuous records of any variable star in the sky. Mu Cephei has also been studied spectroscopically. Since 1943, its spectrum has been used as a standard reference for classifying other stars. Astronomers take the light from a star, split it into its component wavelengths using a spectrograph, and compare the result to known reference stars. Cephei's spectrum is so distinctive that it defines what a cool red supergiant is supposed to look like. If another star's spectrum matches Cephei's, astronomers know immediately what kind of object they're dealing with. That might not sound exciting, but in a field where you can't touch or visit the objects you're studying, having a reliable reference is invaluable. The star's mass is harder to pin down than its size, but estimates place it somewhere between 15 and 25 times the mass of the Sun. That might sound like a lot, but compared to the star's current radius, it's almost nothing. The average density of Cephei is lower than the density of Earth's atmosphere at sea level. If you could somehow scoop out a cubic meter of gas from the star's outer layers, it would weigh less than the air in your living room. The star is so bloated, so spread out, that it barely qualifies as a solid object. It's more like a cloud held together by gravity, a cloud so large that light takes hours to cross it. Cephei will not last much longer, astronomically speaking. The star is already fusing heavier elements in its core. It's working its way down the periodic table, building carbon, oxygen, neon, magnesium, silicon. Eventually, it will hit iron. When that happens, the core will collapse. The outer layers will rebound and explode in a supernova so bright it could briefly outshine the entire galaxy. For a few weeks, Cephei will be visible during the day from Earth, even at 6,000 light-years away. Then it will fade. What's left will either be a neutron star, a ball of matter so dense that a teaspoon of it would weigh as much as a mountain, or a black hole, a region of space where gravity is so strong that not even light can escape. Either way, the red giant phase will be over. The star will have burned out, collapsed, and left behind something far stranger. But Cephei is not the only red supergiant worth talking about. There's another one, closer, brighter, and far more famous. Its name is Antares. If you've ever looked at the night sky in the summer and noticed a bright reddish star sitting low on the southern horizon, you've seen Antares. It's the brightest star in the constellation Scorpius, the scorpion, and it marks the creature's heart. The name Antares comes from ancient Greek. It means rival of Ares, or in Roman terms, rival of Mars. The name makes sense when you see the two objects near each other in the sky. Mars, the red planet, glows with a steady rust-colored light. Antares glows with a similar hue, but it flickers slightly because of atmospheric distortion. To ancient observers, the two looked like competitors, both red, both prominent, both moving through the same region of the sky at different times of year. The Greeks decided that Antares, the star, was challenging Ares, the god of war, for dominance. Antares is a red supergiant. Like Cephei, it has exhausted the hydrogen in its core and expanded to an enormous size. Estimates for its radius vary, but most sources place it somewhere around 700 solar radii. Some studies push it higher, closer to 1,000. The exact number, again, depends on the method and the assumptions built into the model. Measuring the size of a star that sits more than 500 light-years away is not a straightforward process. You can't just point a ruler at it. You have to analyze its light, measure how much energy it's putting out, estimate its temperature, and use those numbers to calculate a radius. Each step introduces uncertainty. Different teams using different data get different results. But the range is consistent enough that we can say with confidence that Antares is huge. Not quite as large as Cephei, but still far larger than the Sun. If you dropped Antares into the center of the solar system, its outer layers would reach past Mars. Earth would be inside it. Venus would be inside it. Mercury would be deep inside it, closer to the core where temperatures are high enough to make the surface layers look cool by comparison. The star would fill the inner solar system. If you were standing on Jupiter, assuming Jupiter survived the swap, Antares would take up more than 40 degrees of the sky. That's 80 times the width of the Sun as seen from Earth. You wouldn't see a disk. You'd see a curved horizon of glowing red stretching from one side of your vision to the other. Antares is also a binary star. It has a companion, a smaller, hotter blue star called Antares B, orbiting at a distance of about 2.9 arc-seconds as seen from Earth. That translates to a physical separation of roughly 550 astronomical units, more than 10 times the distance from the Sun to Pluto. The companion star is dwarfed by Antares A, the red supergiant, but it's still a massive object in its own right, weighing about 7 times the mass of the Sun. The two stars orbit their common center of mass once every roughly 870 years. The companion is difficult to see because Antares A is so bright that its glare drowns out the smaller star, unless you're using a large telescope with excellent optics. The presence of a companion complicates the measurement of Antares A's properties. When you measure the total light coming from the system, you're seeing both stars blended together. Separating their contributions requires careful analysis. That's one reason why estimates of Antares A's luminosity vary so widely. Some sources say the star is about 50,000 times more luminous than the Sun. Others push it closer to 75,000. The difference depends on how much of the system's total light you attribute to the companion versus the primary. Antares is also variable, though not as dramatically as Cephei. Its brightness changes by about half a magnitude over a period of roughly 4 to 5 years. The variations are slow and irregular, driven by the same kind of instability that affects Cephei. The outer layers of Antares expand and contract, the surface temperature shifts, and the amount of light reaching Earth wobbles slightly. The star is close enough and bright enough that these changes can be tracked with backyard telescopes, which has made Antares a favorite target for amateur astronomers who enjoy long-term monitoring projects. The star's mass is estimated at somewhere between 12 and 18 solar masses. That's lighter than Cephei, which makes sense given that Antares is slightly smaller. But even at 12 solar masses, Antares is massive enough that it will end its life in a supernova. The core is already fusing helium into heavier elements. Within the next million years, give or take, the core will collapse and the star will explode. When that happens, Antares will briefly become one of the brightest objects in Earth's sky. For a few weeks, you'll be able to see it during the day. At night, it will cast shadows. Then it will fade, leaving behind either a neutron star or a black hole, and the constellation Scorpius will have a permanent gap where its heart used to be. Both Cephei and Antares are examples of what happens when a massive star runs out of fuel and begins to die. They are not stable, they are not young, they are bloated, unstable, short-lived objects coasting on borrowed time. And yet, despite their instability, despite the fact that they could explode at any moment, astronomically speaking, they are among the largest structures made of ordinary matter in the entire universe, larger than planets, larger than the orbits of planets, so large that the human brain struggles to process the scale even when the numbers are laid out plainly. And here's the uncomfortable part. Cephei and Antares, for all their size, are not even close to the largest stars we've found. They're big, they're impressive, they make excellent introductions to the category of red supergiants, but they are not the record holders, not even close. There are stars out there, sitting in distant reaches of the galaxy, that make Antares look small. Stars that dwarf Mu Cephei the way Mu Cephei dwarfs the Sun. Stars so large that when astronomers first measured them, the results were rejected by peer reviewers who assumed someone had made a calculation error. One of those stars held the title of largest known star for years. Its name appeared in textbooks, documentaries, and popular science articles as the go-to example of stellar extremes. Astronomers pointed to it as the ceiling, the upper limit of how big a star could physically get without tearing itself apart. And then better measurements came in. The numbers changed, and the record holder was quietly, unceremoniously dethroned. That star is called VY Canis Majoris, and its story is where things start to get strange. Chapter 3. The former record holder. VY Canis Majoris's reign. For about 2 decades, if you asked an astronomer to name the largest star in the known universe, they would give you the same answer: VY Canis Majoris. The name showed up in textbooks. It appeared in documentaries narrated by people with soothing British accents. It became the go-to example whenever anyone wanted to illustrate just how absurdly large a star could get, before physics stepped in and said enough. VY Canis Majoris was the monster, the ceiling, the upper limit of stellar gigantism, and for a long time, nobody had any reason to doubt it. Then better instruments came along, more precise measurements, new models, and the number started to shrink. Not because the star got smaller, stars don't do that on human timescales, but because the original estimate, the one that made VY Canis Majoris famous, turned out to be wrong, or at least not quite right, which is a polite way of saying that science had overshot, and the corrections that followed were uncomfortable for everyone who had spent years confidently citing a number that was no longer accurate. This is not a story about failure. It's a story about how hard it is to measure something sitting thousands of light years away when that something is surrounded by a thick cloud of dust, pulsing irregularly, ejecting material into space at random intervals, and refusing to hold still long enough for anyone to get a clean reading. VY Canis Majoris is not a well-behaved star. It is violent, unstable, and shrouded in so much debris that figuring out where the star ends and the surrounding mess begins is more art than science. The star sits in the constellation Canis Major, the greater dog, one of the 2 dogs that follow Orion the Hunter across the winter sky. Canis Major is home to Sirius, the brightest star visible from Earth, a blue-white beacon that dominates the southern sky in January and February. Sirius is what most people think of when they think of that constellation. VY Canis Majoris, by contrast, is dim. You can't see it with your naked eye. It sits at about 7th magnitude, which is well below the threshold of visibility for anyone without a telescope. If you want to find it, you need a decent amateur scope, a clear night, and a star chart showing you exactly where to point. Even then, what you'll see is a faint reddish smudge, nothing that suggests you're looking at one of the most extreme objects in the galaxy. The star was first catalogued on March 7, 1801, by a French astronomer named Jérôme Lalande. Lalande was one of those obsessive 18th century astronomers who spent decades compiling star catalogues, measuring positions, and recording anything that looked vaguely interesting through his telescope. He noted VY Canis Majoris as a 7th magnitude star and moved on. There was nothing in his notes suggesting he thought the object was unusual. To him, it was just another dim star in a crowded sky. He filed it away and kept working. For the next century and a half, VY Canis Majoris sat in the catalogues, unremarkable and mostly ignored. Astronomers occasionally glanced at it, noted that it was red, and moved on to brighter targets. The star's true nature didn't start to become clear until the mid-20th century, when better spectroscopy and photometry revealed that this dim red dot was not a normal star. It was a hypergiant, a star so luminous that even from nearly 4,000 light-years away, it was pumping out enough light to register on photographic plates. The distance is important. VY Canis Majoris sits roughly 3,900 light-years from Earth. Some sources round it to 4,000. Either way, the star is far, not by galactic standards. The Milky Way is about 100,000 light-years across, so VY Canis Majoris is still in our neighborhood, relatively speaking. But compared to the nearby stars we're used to looking at, the ones within a few hundred light-years, this thing is distant. And the fact that it's visible at all from that range tells you immediately that something strange is happening. Luminosity is the total amount of energy a star radiates per second. The Sun's luminosity is about 3.8 times 10 to the power of 26 watts. That's the baseline. A normal red dwarf might have a luminosity 1/10 that of the Sun. A hot blue giant might be 10,000 times brighter. VY Canis Majoris is somewhere between 270,000 and 400,000 times more luminous than the Sun, depending on which study you trust. Even at the lower end of that range, the star is pumping out enough energy every second to make the Sun look like a candle next to a searchlight. That energy is not coming from a small hot surface like the Sun's. VY Canis Majoris is cool. Its surface temperature sits somewhere below 4,000 Kelvin. For comparison, the Sun's surface is about 5,700 Kelvin. The star is cooler, which is why it glows red instead of white or blue. But it has so much surface area that even at that lower temperature, it radiates an almost incomprehensible amount of power. The star is not burning hotter, it's just bigger. Much, much bigger. The size is where things get tricky. Early estimates, the ones that made VY Canis Majoris famous, put the radius at somewhere around 1,900 to 2,600 solar radii. Some papers pushed it even higher, closer to 3,000. Those numbers, if accurate, would make the star so large that if you dropped it into the center of the solar system, its outer layers would reach past the orbit of Saturn. Light, traveling at 300,000 kilometers per second, would take more than 6 hours to travel once around the star's circumference. A passenger jet flying at a steady 900 kilometers per hour would take more than 1,000 years to circle it. The numbers were staggering. They were also wrong. The problem is that VY Canis Majoris is not a clean, well-defined sphere. It's a mess. The star is surrounded by a thick nebula of gas and dust that it has been ejecting for thousands of years. Some of that material is still glowing, heated by radiation from the star. Some of it has cooled and turned opaque, blocking light from the layers underneath. When you point a telescope at VY Canis Majoris, you're not seeing a sharp edge. You're seeing a fuzzy, irregular cloud with brightness that fades gradually as you move outward from the center. Deciding where the star ends and the surrounding material begins is not straightforward. Different astronomers, using different methods and different definitions of where the edge should be, will get different answers. The most widely accepted modern estimate puts the radius at about 1,420 solar radii. That's still enormous. If you placed VY Canis Majoris at the center of the solar system, its outer layers would extend to somewhere around the orbit of Saturn, maybe a bit past Jupiter depending on the model. Earth would be deep inside it. Mars would be inside it. The asteroid belt would be inside it. If you were standing on Saturn, assuming Saturn somehow survived the swap, you would see the star filling half the sky, a glowing red wall stretching from horizon to horizon. But 1,400 is not 2,600. The revision knocked the star off its pedestal. Canis Majoris was no longer the largest star in the known universe. It was still huge, still one of the largest, but not the largest. The title passed to other candidates, stars with better measurements or fewer complications, and Canis Majoris, for all its size and power, became the former record holder, the star that used to be the biggest until someone checked the math. The revision wasn't the result of a single dramatic discovery. It was the product of years of careful observation using better instruments and more sophisticated models. One of the key tools was interferometry, a technique that combines the light from multiple telescopes to create a virtual telescope with a much larger effective diameter. Interferometry can resolve details on a star's surface that would be impossible to see with a single telescope. By measuring how the star's brightness changes at different wavelengths and different angles, astronomers can build up a picture of its size and shape. The results for Canis Majoris showed that the star was smaller than earlier estimates suggested, though still enormous by any reasonable standard. Part of the confusion comes from the star's variability. Canis Majoris is a semi-regular variable, meaning its brightness changes over time in a pattern that's not quite regular but not completely random either. The star's magnitude fluctuates with a period of about 2,000 days, roughly 5.5 years. During that cycle, the star's outer layers expand and contract, the surface temperature shifts, and the amount of light reaching Earth wobbles. If you measure the star at one point in its cycle, you'll get a different size than if you measure it at another point. The difference can be significant, enough to throw off early estimates that didn't account for the star's pulsations. The variability is driven by instability deep in the star's interior. Canis Majoris is not fusing hydrogen in its core anymore. It burned through that fuel millions of years ago. Now it's fusing heavier elements, helium into carbon and oxygen, carbon into neon and magnesium, working its way down the periodic table in a series of increasingly short-lived burning stages. Each stage releases less energy than the one before it and lasts for a shorter time. The star is running out of options, the core is contracting, the outer layers are expanding, and the whole structure is teetering on the edge of collapse. The star's mass is another source of uncertainty. Estimates range from about 17 solar masses on the low end to 30 or 40 on the high end. That's a huge spread, and it matters because the star's mass determines how it will die. If the mass is on the lower end, Canis Majoris might end its life as a supernova that leaves behind a neutron star. If the mass is higher, the core collapse will produce a black hole instead. Either way, the star doesn't have much time left. In astronomical terms, it could explode tomorrow or 100,000 years from now. Both timescales are effectively zero when you're talking about an object that has already been burning for millions of years. The uncertainty in the mass estimate comes from the same problem that complicates the size measurement. The star is surrounded by so much ejected material that it's hard to separate the star itself from the nebula around it. When you measure the total mass of the system, you're seeing everything. The star, the gas, the dust, the shells of material blown off in past eruptions. Disentangling the contributions requires detailed modeling and a lot of assumptions. Different teams using different models get different results. One of the most striking features of Canis Majoris is how much mass it's losing. The star is shedding material at an extreme rate, somewhere around 30 Earth masses per year. That's not a typo. 30 times the mass of the entire planet you're standing on, ejected into space every single year. The material leaves the star in powerful stellar winds and occasional violent eruptions. Some of it gets blown outward at speeds of tens of kilometers per second. Some of it forms dense clumps and arcs that glow as they're heated by radiation from the star. The result is a chaotic, asymmetric nebula that looks nothing like the smooth, spherical shells you see around more stable stars. The mass loss is not sustainable. At this rate, the star is tearing itself apart. The outer layers are so loosely bound that they're barely held in place by gravity. Every time the star pulsates, it kicks more material into space. Every time it erupts, it loses a chunk of its envelope. Eventually, there won't be enough envelope left to sustain the burning in the core, and the star will collapse. The supernova that follows will briefly outshine the entire galaxy. For a few weeks, VY Canis Majoris will be one of the brightest objects in Earth's sky, visible during the day, casting shadows at night. Then it will fade, and all that will be left is a neutron star or a black hole and a rapidly expanding shell of debris. The debris is already there. Observations with infrared telescopes, which can see through dust that blocks visible light, show a complex structure of arcs, knots, and filaments surrounding the star. Some of these features are symmetric, suggesting they were ejected in a steady wind. Others are irregular, evidence of explosive events. One particularly large arc sits about half a light-year from the star, material blown off in an eruption that happened roughly 1,000 years ago. The arc is still glowing, heated by ultraviolet radiation from VY Canis Majoris. It's moving outward at about 30 kilometers per second. In another few thousand years, it will have faded into the background and become indistinguishable from the interstellar medium. The violence of VY Canis Majoris is typical of hypergiant stars. Hypergiants are the rarest and most extreme stars in the galaxy. They sit at the very top of the Hertzsprung-Russell diagram, the chart astronomers use to classify stars by their temperature and luminosity. There are only a handful of confirmed hypergiants in the Milky Way. All of them are unstable. All of them are losing mass. All of them are in the final stages of their lives, coasting toward collapse. VY Canis Majoris is one of the best studied examples because it's relatively close and relatively bright, but it's not unique. There are other hypergiants out there with similar properties, and some of them are probably even larger. Measuring the size of a star like VY Canis Majoris is not like measuring the size of a planet. Planets have surfaces. You can see where the surface ends and space begins. Stars, especially cool, bloated ones like hypergiants, don't have surfaces in the same sense. The density of the star's outer layers fades gradually as you move outward. At some point, the density drops low enough that the gas is effectively part of the surrounding nebula rather than part of the star. But that transition is smooth, not sharp. There's no clear boundary. Astronomers have to pick a definition, some cutoff point where they decide the star ends. Different definitions give different radii. That's why you'll see different numbers in different sources. One common definition is the photosphere, the layer where the star becomes opaque to visible light. Below the photosphere, you can't see into the star. Above it, you're looking at transparent gas or empty space. The radius of the photosphere is a reasonable proxy for the star's size, and it's the number most astronomers use when they quote a radius. But even the photosphere is fuzzy for a star like VY Canis Majoris. The opacity changes with wavelength. The star looks bigger in some colors than in others. Infrared observations, which see deeper into cool gas, give a different radius than observations in visible light. Another complication is the star's shape. VY Canis Majoris is not perfectly spherical. The mass loss is asymmetric, with more material leaving the star in some directions than others. The star's rotation, though slow, creates a slight equatorial bulge. The pulsations distort the surface. When you measure the radius, you're getting an average. The actual distance from the center to the outer edge depends on which direction you're measuring. Some parts of the star stick out farther than others. All of this uncertainty is why the record for largest star keeps changing. It's not that the stars are changing, it's that our measurements are getting better, and our understanding of what we're measuring is getting more refined. Early observations of VY Canis Majoris were done with instruments that couldn't resolve the star's disk. Astronomers had to estimate the size based on the star's luminosity and temperature, plugging those numbers into models that assumed a smooth, spherical surface. Those assumptions were reasonable given the data available at the time, but they weren't quite right. As instruments improved, the models got more sophisticated and the uncertainties shrank. The new numbers were more accurate, but also less dramatic. That's the uncomfortable truth about science. Sometimes the answer changes, not because the universe changed, but because we got better at asking the question. VY Canis Majoris is still one of the largest stars we know about. It's still a hypergiant, still pumping out hundreds of thousands of times the sun's luminosity, still shedding mass at a rate that will tear it apart within the next few 100,000 years. It just isn't the largest. That title belongs to something else now, another red supergiant sitting in another distant corner of the galaxy, waiting for its own measurements to be revised. The story of VY Canis Majoris is a reminder that stellar astronomy is hard. You can't visit these objects. You can't touch them. You can't send a probe to fly past and take pictures. All you have is light, photons that have traveled thousands of years to reach your telescope, carrying encoded information about the object that emitted them. Decoding that information requires careful analysis, sophisticated models, and a willingness to revise your conclusions when new data comes in. Sometimes the new data confirms what you thought. Sometimes it doesn't. Either way, the process moves forward. And the process has moved forward. VY Canis Majoris had its moment as the record holder. It appeared in the Guinness Book of World Records. It was featured in planetarium shows. It became the benchmark against which other large stars were compared. Then the measurements improved, the title changed hands, and VY Canis Majoris became a footnote. Not because it stopped being remarkable, because something even more remarkable took its place. That something was called Scuti, and for a while it looked like the new ceiling, the new upper limit, the star that would finally answer the question of how large a star could get before physics said no. Except physics had other ideas. VY Canis Majoris had its run. For years it sat at the top of the list, the go-to answer whenever anyone asked which star was the largest. Then the measurements got better, the numbers came down, and the title passed to someone new. That someone was Scuti, a red supergiant sitting in the constellation Scutum, the Shield, one of the faintest and least recognizable constellations in the entire sky. Most people have never heard of Scutum. It's a small grouping of dim stars wedged between Aquila the Eagle and Sagittarius the Archer, sitting right in the plane of the Milky Way, where the background star field is so dense that picking out individual constellations becomes an exercise in frustration. And tucked into that crowded field, invisible to the naked eye, barely visible even with binoculars, is a star so large that for a while astronomers thought it might be the upper limit. The biggest thing a star could become before physics stepped in and said stop. The name Scuti comes from the variable star designation system. UY is the identifier, Scuti is the genitive form of scutum, meaning of the shield. It's the kind of name that tells you immediately this is not a bright, famous star with a proper name handed down from ancient civilizations. This is a catalogue entry, a number on a list, something noticed by 20th century astronomers with access to photographic plates and enough patience to scan through thousands of dim stars looking for anything unusual, and Scuti is unusual, not because of its brightness. From Earth, it sits at around magnitude 8 to 10, depending on where it is in its pulsation cycle. That's far too dim to see without a telescope, but in terms of sheer physical size, Scuti is a monster. Or at least it was, for a while, until the numbers got revised and the monster shrank. Let's start with the version of the story that made Scuti famous. The version that appeared in pop science articles, YouTube videos, and list-based websites with titles like 10 Stars That Will Blow Your Mind. The version that put Scuti in the Guinness Book of World Records as the largest known star. The early measurements, the ones that made headlines, put the star's radius at somewhere around 1,700 solar radii. Some sources pushed it even higher, closer to 1,900. Those numbers were enormous. If you took Scuti and dropped it into the center of the solar system where the Sun currently sits, the star's outer layers would extend past the orbit of Jupiter. Saturn would be inside it. Uranus might be grazing the edge. The star would fill the inner solar system like water filling a bathtub, and everything inside that radius would be submerged in glowing red gas hot enough to vaporize rock. 1,700 solar radii, that's roughly 7.9 astronomical units. Light, traveling at 300,000 kilometers per second, would take about 4.5 hours to travel from the star's core to its surface. A passenger jet flying at 900 kilometers per hour would take more than 800 years to make the same trip. If you could somehow stand at the center of Scuti and look outward, you wouldn't see a surface, you'd see layers. Glowing gas stretching in every direction for millions of kilometers, fading gradually from bright red near the core to dim, almost invisible haze at the outermost edges. You would be inside a star the way a fish is inside an ocean, surrounded on all sides by something so vast that the concept of an edge becomes meaningless. Those early measurements were based on a combination of the star's luminosity, its temperature, and its distance from Earth. Astronomers knew Scuti was bright in absolute terms, pumping out hundreds of thousands of times more light than the Sun. They measured the star's surface temperature using spectroscopy, analyzing the light to see which wavelengths were strongest. Red supergiants are cool stars, at least by stellar standards, and Scuti's spectrum showed that its surface temperature sat somewhere around 3,300 to 3,500 Kelvin. Plug those numbers into the equations governing blackbody radiation, assume the star is a sphere, and you can calculate the radius. The result, based on the data available in the early 2010s, came out to around 1,700 solar radii, maybe more. The uncertainty was large because the distance to Scuti was uncertain, but the ballpark figure was enough. Scuti became the new record holder, the largest known star in the universe. Except there was a problem, a big one, and it had to do with distance. Scuti sits roughly 5,800 light-years from Earth. That's the modern estimate, the one derived from data collected by the European Space Agency's Gaia spacecraft, a mission that spent years measuring the positions and distances of more than 1 billion stars with unprecedented precision. Gaia used parallax, the apparent shift in a star's position as Earth moves around the Sun, to calculate distances far more accurately than previous methods. When Gaia's data became available, astronomers went back and recalculated the properties of thousands of stars, including Scuti. And when they ran the numbers again using the improved distance measurement, the size estimate came down, way down. The new figure, published in a 2023 study, put the radius at about 909 solar radii. Still enormous, still one of the largest stars we know about, but not 1,700, not even close. 909 solar radii. That's about 4.2 astronomical units. If you placed Scuti at the center of the solar system, Its outer layers would reach somewhere between the orbits of Mars and Jupiter. Earth would still be inside it. Venus and Mercury would be deep inside it, closer to the core where the density is higher and the temperature climbs. But Saturn would be safely outside. Uranus would be outside. The star, while still massive, would no longer dominate the entire solar system. It would fill the inner region and stop. That's the difference between 1700 solar radii and 900. One version swallows half the solar system. The other stops at the asteroid belt. So what happened? Did the star shrink? No. Stars don't shrink on human timescales, at least not in any way that would show up in measurements taken a decade apart. The star is the same size it was in 2010. What changed was the measurement, specifically the distance measurement. Distance is the foundation of almost every calculation in astronomy. If you get the distance wrong, everything downstream of that number shifts. Luminosity depends on distance. If a star looks faint but you think it's close, you'll calculate a low luminosity. If you later realize it's farther away than you thought, the luminosity goes up because the star must be intrinsically brighter to appear that faint from that range. Radius depends on luminosity. If the luminosity changes, the radius changes. Get the distance wrong by a factor of 2 and the radius estimate can shift by 50% or more. The early distance estimate for Scuti was based on less precise methods than what Gaia provided. Before Gaia, astronomers used a combination of techniques to estimate distances to faraway stars. Spectroscopic parallax, which sounds like it measures parallax but doesn't, estimates distance by comparing a star's spectrum to known templates and inferring how far away it must be to produce the observed brightness. Kinematic distance estimates use the star's motion through space to guess how far it is. Both methods are useful, but both come with large uncertainties, especially for stars sitting thousands of light-years away in dusty regions of the galaxy where intervening material scatters and absorbs light. Scuti sits in the plane of the Milky Way, right in the thick of the galactic disk where dust is dense and light doesn't travel cleanly. Early estimates placed the star somewhere between 4,500 and 9,500 light-years away. That's a huge range, and it translates directly into a huge range in calculated radius. Gaia changed the game. The spacecraft measured parallaxes for stars out to several thousand light-years, with precision measured in milliarseconds. For Scuti, Gaia's data gave a distance of roughly 5,870 light-years, give or take a few hundred. That number is far more precise than anything available before Gaia launched. When astronomers plugged the new distance into their models, the radius estimate dropped. Not because the models changed, because the input data got better. The star was farther away than earlier estimates suggested, which meant it didn't need to be as intrinsically luminous to produce the observed brightness. Lower luminosity at the same temperature means smaller radius. The math is straightforward. The result was uncomfortable for everyone who had spent years citing 1700 solar radii as a fact. The luminosity estimate also came down. Early figures put Scuti at around 340,000 times the Sun's luminosity. The revised estimate, using Gaia's distance and improved photometry from the 2-micron all-sky survey, dropped that number to about 124,000 solar luminosities, still enormous, still in the hypergiant range, but not the absurd record-breaking figure that made Scuti famous. 124,000 solar luminosities means the star is bright enough that if you placed it where the Sun is, Earth would be instantly incinerated. The surface would vaporize, the oceans would boil off into space within seconds. The atmosphere would be stripped away by radiation pressure. But it's not 340,000. The difference matters. temperature estimates shifted slightly too. The older value of 3365 Kelvin was revised upward to about 3550 Kelvin in the 2023 study. That's a small change, only a few percent, but it's enough to affect the calculated radius. Hotter stars radiate more energy per unit area, which means a given luminosity can be produced by a smaller surface. The combination of lower luminosity and slightly higher temperature both push the radius downward. The result is 909 solar radii instead of 1700. Still a giant. Still one of the top contenders for largest known star, just not the undisputed champion. Scuti is also a variable star, which complicates the measurements even further. The star's brightness changes over time, fluctuating between magnitude 8.29 and 10.56 over a rough period of 740 days. That's about 2 years. During that cycle, the star's outer layers expand and contract. The surface temperature shifts. The amount of light reaching Earth wobbles. If you measure the star's brightness at the peak of its cycle, you'll get a different apparent magnitude than if you measure it at the trough. That difference affects the calculated luminosity, which affects the calculated radius. Some of the variation in published size estimates for Scuti comes from the fact that different studies used observations taken at different phases of the star's pulsation cycle. The star doesn't have a single fixed radius. It has a range. 909 solar radii is the average, or close to it, but the actual value moves up and down as the star breathes. The variability is typical of red supergiants and hypergiants. These stars are not stable. They sit near the upper right corner of the Hertzsprung-Russell diagram, a region where stars are cool, luminous, and teetering on the edge of collapse. The outer layers are so loosely bound that they barely qualify as part of the star. Gravity is weak at those distances. Radiation pressure from the core pushes outward. The two forces are almost balanced, which means small changes in the core's energy output can cause the outer layers to swell or contract by large amounts. Scuti swells and shrinks, sheds mass in powerful stellar winds, and occasionally ejects clumps of material in violent outbursts. The star is not a stable sphere. It's a chaotic, asymmetric cloud of gas held together by gravity and barely managing to keep itself from flying apart. The mass of Scuti is another source of uncertainty. Estimates range from about 7 to 10 solar masses on the low end to as high as 25 solar masses on the high end, depending on which model you use and which assumptions you make. That's a huge spread, and it matters because the star's mass determines its future. Lower mass red supergiants end their lives as supernovae that leave behind neutron stars. Higher mass ones produce black holes. The difference between 7 solar masses and 25 solar masses is the difference between two completely different kinds of remnants. Unfortunately, measuring the mass of a single isolated star like Scuti is extremely difficult. You can estimate it based on the star's luminosity and evolutionary models, but those models come with large uncertainties. You can try to measure the star's gravitational influence on nearby objects, but Scuti doesn't have a visible companion star or planets we can detect. The mass estimate is essentially an educated guess. One thing is certain: Scuti is losing mass. The star is shedding its outer layers in a stellar wind at a rate of somewhere around 1 solar mass every few 100,000 years. That might not sound fast, but it adds up. Over 1 million years, the star loses several times the mass of the Sun. That material doesn't vanish. It spreads out into the surrounding space, forming a nebula of gas and dust that eventually mixes into the interstellar medium. The nebula around Scuti is too faint to see in visible light, but infrared telescopes can pick it up. The material glows faintly, heated by radiation from the star, and shows the same kind of asymmetric structure seen around other hypergiants. Clumps, arcs, and streamers of gas stretch outward in irregular patterns, evidence of a violent, chaotic process that's been running for thousands of years. The dust around UY Scuti is one reason why the early size estimates were off. Dust absorbs and scatters light, especially at shorter wavelengths like blue and ultraviolet. When you look at UY Scuti through a telescope, you're not seeing all the light the star emits. Some of it gets blocked by intervening dust, both in the star's immediate neighborhood and in the broader region of the Milky Way between us and the star. The result is that the star looks dimmer and redder than it actually is. Astronomers call this extinction and reddening. To correct for it, you have to estimate how much dust is in the way and adjust the observed brightness accordingly. Different studies use different extinction estimates, which leads to different luminosity estimates, which leads to different radius estimates. The better your model of the dust, the better your size calculation. Gaia's data helped, but dust is still a major source of uncertainty for stars like UY Scuti that sit deep in the galactic plane. UY Scuti's location makes things harder. The star sits in Scutum, right in the middle of the Milky Way's most densely packed star fields. This region is sometimes called the Scutum star cloud, and it's one of the brightest patches of the galaxy as seen from Earth. When you look at that part of the sky with a telescope, you see thousands of stars packed into a small area. Picking out UY Scuti from the crowd requires precise coordinates and a good finder chart, and because the background is so crowded, measuring the star's properties accurately is tricky. You have to make sure you're measuring light from UY Scuti and not from a nearby foreground or background star that happens to be sitting close to the same line of sight. Contamination from neighboring stars can throw off photometry, especially if the stars are close enough that their light blends together in low-resolution images. Another complication is that UY Scuti is a cool star, and cool stars emit most of their light in the infrared rather than in visible wavelengths. Infrared observations are essential for getting accurate data on stars like this, but infrared light doesn't penetrate Earth's atmosphere as well as visible light does. Water vapor in the atmosphere absorbs certain infrared wavelengths, which means ground-based infrared telescopes have to work around those absorption bands or use instruments at high, dry sites where the atmosphere is thinner. Space-based infrared telescopes like Spitzer and the James Webb Space Telescope don't have that problem, but they're expensive and their observing time is highly competitive. Not every astronomer who wants to study UY Scuti gets a chance to use those instruments. The result is that much of the data on UY Scuti comes from ground-based observations that have to be carefully corrected for atmospheric effects. The 2023 study that revised UY Scuti's radius used data from the 2-micron all-sky survey, a project that mapped the entire sky in near-infrared wavelengths. Near-infrared light penetrates dust better than visible light, which makes it ideal for studying stars in dusty regions like the galactic plane. The study combined 2-micron all-sky survey photometry with Gaia's distance measurement and ran the numbers through updated models of stellar atmospheres. The result was a radius of 909 solar radii, a luminosity of 124,000 solar luminosities, and a temperature of 3,550 Kelvin. The uncertainties were still large, but the central values were far more reliable than the earlier estimates. And those central values knocked UY Scuti off its pedestal. The demotion of UY Scuti is a case study in how science works. Not the idealized version where everyone agrees and the truth is revealed in a single elegant experiment, but the messy, iterative version where measurements get revised, models get updated, and the answer changes every time someone builds a better instrument. Science is not a list of facts. It's a process, a method for refining guesses into better guesses. Early astronomers looked at Scuti, measured its brightness, estimated its distance, and calculated a radius of 1700 solar radii. They weren't lying, they weren't incompetent, they were working with the best data they had at the time. Then Gaia launched. Better distance measurements became available. Someone went back and recalculated. The new answer was 909 solar radii. That doesn't mean the old answer was worthless. It means the new answer is more accurate. And 20 years from now, someone will probably go back and recalculate again using even better data, and the answer will shift once more. That's how this works. The public-facing version of the story, the one that shows up in clickbait articles and list videos, doesn't handle revisions well. Once a star gets labeled as the biggest, that label sticks. Even after the measurements change, even after the title passes to someone else, the old claim lingers. You can still find sources today that describe Scuti as the largest known star, citing 1700 solar radii, even though that number has been outdated for years. The corrections don't propagate as fast as the original headlines. The result is a kind of informational inertia, where the popular understanding lags behind the actual science by a decade or more. Scuti is still enormous. 909 solar radii is not a small number. The star is roughly 4 times the size of Canis Majoris, using the revised estimates for both. If you placed Scuti at the center of the solar system, it would swallow everything inside the orbit of Mars. That includes Earth, Venus, and Mercury. The asteroid belt would be inside it. Some of the inner gas giants' moons would be inside it. A sphere that size, made of glowing gas, would fill your entire field of view if you were standing on Jupiter. The star would subtend an angle of more than 20 degrees across the sky. For comparison, the Sun, as seen from Earth, subtends about half a degree. Scuti, from Jupiter's orbit, would look 40 times wider. You wouldn't see a disk, you'd see a curved horizon of red light, fading into darkness at the edges, stretching from one side of your vision to the other. That's the scale we're talking about, even with the revised numbers. But 909 solar radii is not 1700. The difference is roughly half. The star that was supposed to be the biggest turned out to be only half as big as people thought. That's not a rounding error, that's a fundamental revision, and it raises an uncomfortable question. If Scuti's size was wrong, what else is wrong? How many other stars are sitting in catalogues with inflated size estimates because the distance measurements were off, or the dust corrections were incomplete, or the models didn't account for variability? How many record holders are waiting to be dethroned by the next generation of instruments? The answer is probably more than a few. Stellar astronomy is hard. You're trying to measure objects that are thousands of light years away, surrounded by dust, often variable, sometimes asymmetric, always faint. You can't visit them, you can't send a probe, all you have is light, and the light you're seeing left the star hundreds or thousands of years ago. It's old news by the time it reaches you, and you have to decode that old news using models that assume the star behaves in certain ways, has certain properties, fits certain categories. When the models are wrong, the results are wrong. When the data improves, the results change. That's not a bug. That's the system working exactly as it's supposed to. Scuti's story is also a reminder that the universe doesn't care about records. The star is not trying to be the biggest. It's not competing with Canis Majoris or Antares or any other giant. It's just a massive star in the late stages of its life, fusing heavier elements in its core, shedding mass into space, and coasting toward the inevitable collapse that will end in a supernova. Whether humans measure it correctly or not makes no difference to the star. Scuti will explode when its core runs out of fuel, and that explosion will briefly outshine the galaxy whether the star's radius is 900 solar radii or 1700. The record is a human construct. The star is just doing what stars do, and yet the record matters, not because the universe cares, but because we do. Humans are obsessed with extremes. The biggest, the smallest, the fastest, the oldest, the farthest. We want to know where the limits are. We want to find the edges, and when we find something that looks like an edge, we measure it, name it, and hold it up as an example. Scuti was that example for a while. Then the measurements improved, the edge moved, and the example became a cautionary tale. The star that was supposed to be the limit turned out to be just another step on the way to something even larger, something sitting in a distant star cluster, barely studied, almost forgotten, until someone pointed a telescope at it and realized what they were looking at. That something is called Stephenson 218, and as of right now, it's the largest star we've ever confirmed. Whether it will stay that way is another question entirely. Scuti had its moment. Then the measurements came in, the radius dropped, and the throne sat empty. Not for long, because sitting in a distant corner of the galaxy, tucked inside a dense stellar cluster most people have never heard of, surrounded by so much dust and crowding that it took decades for anyone to realize what they were looking at, is a star so large that when astronomers first calculated its size, they went back and checked their math 3 times to make sure they hadn't made a mistake. They hadn't. The number was real. The star was real, and the number was so absurd that it broke every intuitive sense of scale anyone had built up from years of studying red supergiants. The star is called Stephenson 218, and as of right now, it is the largest confirmed star in the known universe. Let's get the number out of the way first, because if you don't hear it now, you'll spend the rest of this chapter waiting for it. The radius of Stephenson 218 is approximately 2,149 solar radii. 2,149. That is not a typo. That is not a preliminary estimate waiting for revision. That is the current best measurement based on the most recent data available. 2,149 times the radius of our Sun. If you placed Stephenson 218 at the center of the solar system where the Sun currently sits, the star's outer layers would extend roughly to the orbit of Saturn. Not near Saturn, not past Saturn, right at Saturn. The planet would be sitting at the edge of the star's photosphere, grazing the outer layers of glowing red gas. Everything inside that orbit, Jupiter, Mars, Earth, Venus, Mercury, the asteroid belt, every comet, every speck of dust, all of it would be submerged inside the star, gone, vaporized, mixed into the outer envelope of a dying giant that has swollen to a size so extreme it challenges the upper limits of what stellar physics says should be possible. 2,149 solar radii. That translates to roughly 1.5 billion kilometers. If you prefer a comparison that doesn't involve numbers with 9 digits, think of it this way. Light, traveling at 300,000 kilometers per second, takes about 8 minutes and 20 seconds to travel from the Sun to Earth. Light leaving the core of Stephenson 218 would take roughly 2.5 hours to reach the star's surface. 2.5 hours, that's longer than most movies. You could start a film, watch the entire thing, and light would still be fighting its way outward through layers of plasma so thick, and so diffuse that every photon gets scattered trillions of times before it finally escapes into space. The volume is even more ridiculous. Volume scales with the cube of the radius, which means small changes in radius produce enormous changes in volume. Stephenson 218's volume is roughly 10 billion times the volume of the Sun. 10 billion. You could fit 10 billion suns inside Stephenson 218 and still have room left over. If you tried to fill the star with Earths instead, you'd need about 13 quadrillion of them. That's 13 followed by 15 zeros. There are not that many Earths. There are not that many planets. If you took every rocky body in the solar system, every planet, every moon, every asteroid, ground them all up and packed them into Stephenson 218, you wouldn't even notice. The star would swallow them without a flicker. And yet from Earth, Stephenson 218 is completely invisible. You cannot see it with your naked eye. You cannot see it with binoculars. You can barely see it with a decent amateur telescope. The star sits at a distance of roughly 19,000 light-years, tucked deep inside a cluster called Stephenson 2, located in the constellation Scutum, the same constellation that hosts UY Scuti, incidentally, which tells you something about that part of the sky. Scutum sits right in the plane of the Milky Way, in one of the densest regions of the galactic disk. When you point a telescope at Scutum, you see stars, thousands of them, packed so tightly together that separating individual objects becomes a challenge. And buried in that crowd, hidden behind layers of interstellar dust, dimmed by distance and extinction, is the largest star we have ever confirmed. The cluster itself, Stephenson 2, is a young open cluster. Young in astronomical terms, meaning it formed somewhere between 10 and 20 million years ago. That's recent. The dinosaurs went extinct 66 million years ago. Stephenson 2 is younger than the Himalayas. It's a loose grouping of massive stars, all born from the same giant molecular cloud, all sitting roughly the same distance from Earth. Open clusters like this are common in the Milky Way. They're the nurseries where massive stars are born, live fast and die young. Most of the stars in Stephenson 2 are hot, blue and burning through their fuel at ferocious rates. A few have already evolved off the main sequence and swollen into red supergiants. Stephenson 218 is one of those red supergiants, and it is by far the largest object in the cluster. The cluster was first catalogued by Charles Bruce Stephenson, an American astronomer working at the Warner and Swasey Observatory in the 1960s and 70s. Stephenson spent years surveying the Milky Way in the infrared, looking for clusters and associations of massive stars that were too obscured by dust to show up clearly in visible light surveys. Infrared light penetrates dust better than visible light, which makes it the tool of choice for studying objects in the galactic plane where extinction is high. Stephenson identified the cluster in 1990, published his findings, and moved on. The cluster was catalogued. The stars were noted, and for more than a decade, nobody paid much attention to it. Then in 2006, a team of astronomers, led by Fiona Riddick at the University of Central Lancashire, decided to take a closer look. They used infrared spectroscopy to analyze the light from several stars in the cluster, measuring their temperatures and luminosities to figure out what kind of objects they were dealing with. Most of the stars were exactly what you'd expect in a young, massive cluster. Hot blue supergiants, a few yellow supergiants, some red supergiants in the process of dying, but a handful of the red supergiants stood out. They were unusually luminous, way more luminous than red supergiants in other clusters of similar age. The team flagged them as potential hypergiants, stars at the very top of the luminosity scale, and recommended follow-up observations. Stephenson 218 was one of those flagged objects. It wasn't the brightest star in the cluster, not by a long shot, That honor went to several blue supergiants that outshone it by factors of 10 or more. But when the team calculated the star's bolometric luminosity, the total energy output across all wavelengths, they got a number that didn't make sense, roughly 440,000 times the sun's luminosity. 440,000. That's hypergiant territory. That's the kind of luminosity you get from stars at the absolute upper edge of what's physically possible. And when you combine that luminosity with the star's surface temperature, which spectroscopy pegged at around 3600 Kelvin, and plug both numbers into the standard equation for stellar radius, you get a result that seems like it has to be wrong. The equation is straightforward. Luminosity equals 4 pi times the radius squared times the Stefan-Boltzmann constant times the temperature to the 4th power. Solve for radius, and you get radius equals the square root of luminosity divided by 4 pi sigma t to the 4th. Plug in 440,000 solar luminosities, plug in 3600 Kelvin. Run the math. The radius comes out to about 2,149 solar radii. The first time someone ran that calculation, they probably assumed they'd dropped a decimal point. They went back, checked the luminosity, checked the temperature, checked the distance to the cluster. Everything held. The number was real. Stephenson 218 was not just large, it was larger than anything anyone had ever measured. But here's the problem. Measuring the size of a star like Stephenson 218 is not as simple as pointing a telescope, taking a picture, and reading off a number. You can't resolve the star's disk. Even with the best telescopes on Earth, Stephenson 218 is so far away that it looks like a point source, a single pixel. You can measure its brightness, you can analyze its spectrum, but you can't directly see its size. The radius estimate comes entirely from the Stefan-Boltzmann equation, which means it depends on two things, luminosity and temperature. If you get either of those wrong, the radius estimate shifts. And both luminosity and temperature measurements come with large uncertainties, especially for stars sitting 19,000 light-years away in dusty regions of the galaxy. Start with luminosity. To calculate a star's luminosity, you need to know how much light it's emitting in total, not just the light reaching Earth. That means you have to correct for distance and extinction. Distance determines how much the light has spread out by the time it reaches you. Extinction accounts for how much light has been absorbed or scattered by dust along the way. Both corrections require accurate measurements. The distance to Stephenson 2 is estimated at about 19,000 light-years, but that number comes with an uncertainty of plus or minus a few thousand light-years. The exact distance depends on which method you use and which assumptions you make. Kinematic distances, derived from the cluster's motion through the galaxy, give one answer. Spectroscopic distances, based on comparing the cluster's stars to similar objects with known distances, give another. The two methods don't always agree. A difference of 2,000 or 3,000 light-years in the distance estimate translates directly into a difference of 50% or more in the calculated luminosity. Get the distance wrong, and the luminosity estimate shifts. Get the luminosity wrong, and the radius estimate shifts. Extinction is even trickier. Stephenson 2 sits in the galactic plane, right in the thick of the Milky Way's disk where dust is dense. The light from the cluster has to travel through 19,000 light-years of that dust before it reaches Earth. Along the way, some of it gets absorbed, some of it gets scattered. The shorter the wavelength, the more it gets affected. Blue and ultraviolet light get hit hardest. Red and infrared light make it through more easily. The result is that when you look at Stephenson 218 through a telescope, the star looks dimmer and redder than it actually is. To get the true luminosity, you have to estimate how much light was lost and add it back. That estimate depends on models of interstellar dust, which are based on observations of other regions of the galaxy. The models are good, but they're not perfect. Different models give different extinction estimates. A difference of 1 magnitude in extinction, which is well within the uncertainty range for a star like Stephenson 218, changes the calculated luminosity by a factor of about 2.5. That's enormous. And it propagates directly into the radius estimate. Temperature is the other half of the equation. To measure a star's surface temperature, astronomers use spectroscopy. They split the star's light into its component wavelengths and look for absorption lines, dark gaps in the spectrum where specific elements in the star's atmosphere have absorbed light at specific wavelengths. The pattern of absorption lines acts like a fingerprint. Different temperatures produce different patterns. By comparing the observed spectrum to libraries of reference spectra from stars with known temperatures, astronomers can estimate the temperature of the star they're studying. For cool red supergiants like Stephenson 218, the dominant absorption lines come from molecules like titanium oxide and water vapor. The strength of those lines depends on temperature. Stronger lines mean cooler temperatures. Weaker lines mean hotter temperatures. The problem is that the relationship is not perfectly clean. The strength of a molecular absorption line also depends on the density and composition of the star's atmosphere, both of which are hard to measure. Small differences in how you model the atmosphere can lead to differences of a few hundred Kelvin in the temperature estimate. A difference of 300 Kelvin applied to a star with a temperature of 3600 Kelvin changes the calculated radius by about 20%. That's the difference between 2100 solar radii and 1700. Get the temperature slightly wrong and the radius estimate moves by hundreds of solar radii. So when you see a published radius of 2149 solar radii for Stephenson 218, understand that the number comes with a large error bar. The actual radius could be anywhere from about 1800 to 2500 solar radii depending on which combination of luminosity and temperature estimates you trust. That range is huge. But even at the low end, even at 1800 solar radii, Stephenson 218 is still larger than any other star we've measured. The error bars on UY Scuti, on VY Canis Majoris, on mu Cephei, they all overlap with each other. Their rankings could shift depending on which study you cite. Stephenson 218 sits above all of them. It is not a close race. The star is unambiguously the largest we've found. The reason Stephenson 218 took so long to identify has everything to do with its location. Sitting inside a dense stellar cluster surrounded by hundreds of other stars, buried under layers of interstellar dust, the star is easy to miss. In visible light, Stephenson 218 barely registers. The extinction is so severe that most of the star's light gets absorbed before it reaches Earth. What little makes it through is dim, faint, unremarkable. If you pointed a visible light telescope at the cluster and tried to pick out Stephenson 218 from the crowd, you'd have a hard time. It looks like dozens of other red stars scattered across the same patch of sky. There's nothing about its visible appearance that screams largest star in the galaxy. It's only when you switch to infrared wavelengths, where dust is more transparent and the star's true brightness becomes apparent, that Stephenson 218 stands out. Infrared surveys revealed that this dim red dot was pumping out hundreds of thousands of times more energy than the Sun. That discovery triggered follow-up spectroscopy. Spectroscopy revealed the star's temperature. Temperature plus luminosity gave the radius, and the radius turned out to be 2149 solar radii. The crowding didn't help either. Open clusters are messy environments. Stars sit close together, at least by astronomical standards. When you're trying to measure the brightness of a single star in a cluster, You have to make sure you're not accidentally including light from nearby stars in your measurement. If the stars are close enough on the sky that their light blends together, your photometry will be contaminated. You'll measure a combined brightness instead of the brightness of the individual star you care about. For Stephenson 218, sitting in a cluster with hundreds of members, contamination was a real concern. Early observations had to be done carefully, using high-resolution infrared imaging to isolate the star from its neighbors. Even then, the measurements came with uncertainties. Some of the light reaching the detector was almost certainly coming from other stars sitting along the same line of sight. How much? Hard to say. Enough to matter? Probably not, but the possibility can't be ruled out completely. The discovery of Stephenson 218 is also a reminder that the galaxy is full of objects we haven't found yet. Open clusters are relatively easy to spot. They're bright, they're dense, and they stand out against the background of the Milky Way. But individual stars, especially dim ones buried in crowded fields, are easy to overlook. Before infrared surveys became routine, objects like Stephenson 218 were invisible. They didn't show up in photographic plates. They didn't make it into catalogues. They were there, shining away, pumping out hundreds of thousands of times the sun's luminosity, and nobody noticed. It's only in the last few decades, with the advent of large-scale infrared surveys like 2-micron all-sky survey and the Wide-Field Infrared Survey Explorer, that astronomers have been able to systematically search for these hidden giants. And every time a new survey goes online, a few more show up. Stephenson 218 is the largest we've found so far. It probably won't be the largest we ever find. There's also the question of whether Stephenson 218's size is even stable. Red supergiants and hypergiants are not static objects. They pulsate. Their outer layers expand and contract over timescales of months to years. The star's radius changes as it breathes. Stephenson 218 is variable, though the exact period and amplitude of its variations are not well characterized. The star is too dim and too distant for ground-based telescopes to monitor continuously. What we know about its variability comes from a handful of observations spread across decades. Those observations show that the star's brightness changes, which means its radius changes. The 2149 solar radii figure is an average or a snapshot taken at some specific moment in the star's pulsation cycle. At maximum size, the star could be larger. At minimum size, it could be smaller. The difference could be a few hundred solar radii either way. The star is not a fixed sphere. It's a dynamic, chaotic object that's constantly shifting, and it's dying. Stephenson 218 is not a young star anymore. It has burned through the hydrogen in its core. It has fused helium into carbon and oxygen. It is likely fusing heavier elements in shells around a contracting core, working its way through carbon, neon, oxygen, silicon, building up layers like an onion. Each layer burns hotter and faster than the one before it. The silicon burning phase, the last stage before the core turns to iron, lasts only a few days. Once the core is made of iron, the star is out of options. Iron fusion doesn't release energy, it absorbs it. The core collapses in less than a second. The outer layers rebound off the collapsing core and explode outward in a supernova. For a few weeks, Stephenson 218 will outshine every other star in the galaxy. Then it will fade. What's left will be a neutron star or a black hole, depending on how much mass the core contains at the moment of collapse. Either way, the red supergiant phase will be over. The largest star in the galaxy will vanish, and all that will remain is a compact remnant and a rapidly expanding shell of debris. When will that happen? Nobody knows. The star could explode tomorrow, or 100,000 years from now. Both timescales are effectively zero when you're talking about an object that has been burning for millions of years. Stellar evolution models suggest that stars as massive and as luminous as Stephenson 218 don't last long in the red supergiant phase. A few 100,000 years, maybe 1,000,000 at most. The clock is running. The star is living on borrowed time, and when it finally runs out, the explosion will be visible from Earth even at 19,000 light-years. For a brief moment, Stephenson 218 will be one of the brightest objects in the night sky. Then it will be gone. The existence of Stephenson 218 raises uncomfortable questions about the upper limits of stellar size. For years, astronomers thought there was a ceiling, a point where a star got so large and so luminous that it couldn't hold itself together anymore. Radiation pressure from the core would blow the outer layers away faster than gravity could pull them back. The star would disintegrate. The limit was estimated at around 40,000 to 50,000 solar luminosities. Stephenson 218 is pumping out 440,000. That's nearly 10 times the supposed limit. And it's not disintegrating, it's pulsating, sure. It's losing mass in a stellar wind, but it's not flying apart. It's holding together, at least for now. Which means either the models are wrong, or there's something about red supergiants that we don't understand. One possibility is that the limit isn't a hard ceiling. It's more of a soft boundary that depends on the star's composition, rotation, and magnetic field. Stars with lower metallicity, meaning fewer heavy elements, might be able to push past the limit because their atmospheres are more transparent to radiation. Stars that are rotating slowly might hold together better because rotation adds an extra outward force that can destabilize the outer layers. Stars with strong magnetic fields might channel mass loss in specific directions, creating asymmetric winds that let the star shed mass without tearing itself apart. Stephenson 218 might be threading the needle, sitting right at the edge of instability, shedding mass fast enough to avoid a runaway explosion but slowly enough to keep the star intact. Or the models might just be wrong. That's the other possibility. The equations governing stellar structure are complicated. They involve assumptions about convection, opacity, nuclear reaction rates, and a dozen other variables that are hard to measure directly. Small changes in those assumptions can shift the predicted luminosity limit by large amounts. Maybe the real limit is higher than anyone thought. Maybe there's no limit at all, just a region of parameter space where stars become increasingly rare and increasingly unstable. Stephenson 218 is also a challenge for observational astronomy. The star is faint. It's distant. It's surrounded by dust. Getting accurate measurements requires large telescopes, sophisticated instruments, and a lot of observing time. All of that is expensive. And because Stephenson 218 is not a high-priority target for most research programs, it doesn't get observed very often. The data we have on the star comes from a handful of studies spread across 2 decades. That's not enough to build a detailed picture. We know the star is large. We know it's luminous. We know it's variable. Beyond that, the details are fuzzy. What's the exact pulsation period? What's the mass loss rate? What's the composition of the stellar wind? What's the structure of the nebula surrounding the star? All of those questions are answerable in principle, but answering them requires follow-up observations that nobody has funded yet. Stephenson 218 is the largest known star, but it's also one of the least studied objects in its size class. That's the uncomfortable reality of modern astronomy. The most extreme objects are often the hardest to study because they're rare, distant, and expensive to observe. The star also raises questions about how red supergiants form in the first place. Stephenson 218 started its life as a massive main sequence star, probably somewhere between 20 and 40 solar masses. It fused hydrogen in its core for a few million years, burning through its fuel at a ferocious rate. Then the hydrogen ran out. The core contracted, the outer layers expanded, and over the course of a few thousand years, the star transformed from a hot blue supergiant into a cool red hypergiant. That transformation is not well understood. The models predict it should happen, but the details are murky. How fast does the expansion happen? How much mass does the star lose during the transition? How does the structure of the core change as the star evolves? All of those questions are still open. Stephenson 218 is a snapshot of that process, caught in the act of dying. Studying it in detail could help answer those questions, but again, that requires observations, and observations require funding. And funding requires someone to write a proposal, convince a panel of reviewers that the science is worth doing, and wait months or years for telescope time. Meanwhile, the star keeps pulsating, keeps shedding mass, keeps coasting toward collapse. Comparing Stephenson 218 to the other giants makes the scale shift even more obvious. Antares, at roughly 700 solar radii, would be a dot sitting at the edge of Stephenson 218's core. Vy Canis Majoris, at 1400 solar radii, would fit inside Stephenson 218 with room to spare. Vy Scuti, using the revised estimate of 909 solar radii, would be dwarfed. You could fit more than 10 Ui Scutis across the diameter of Stephenson 218. The Sun, at 1 solar radius, is so small in comparison that trying to visualize it next to Stephenson 218 is pointless. If the Sun were a marble, Stephenson 218 would be a hot air balloon the size of a city block. If the Sun were a grain of sand, Stephenson 218 would be a beach ball. The metaphors break down because the scale is too extreme. Nothing in human experience maps onto a 2,000-fold difference in size. You can stack comparisons, you can draw diagrams, you can write out the numbers, and none of it will make the size feel real. Your brain will process the information, file it away, and move on. Because 2,149 solar radii is not a size humans can intuit, it's just a number. But here's what isn't just a number. Stephenson 218 exists, right now, at this exact moment, 19,000 light-years from Earth. There is a star so large that if you could somehow stand on its surface and look around, you wouldn't see a horizon. You'd see a flat plane of glowing gas stretching outward in every direction until it faded into darkness. The curvature would be too gentle to detect. The star would look infinite. And somewhere deep below that surface, buried under layers of plasma so thick that light takes hours to escape, is a core where silicon is fusing into iron, ticking down the final hours of the star's life. When that core collapses, the explosion will be visible from Earth, even through 19,000 light-years of dust. For a few weeks, we'll have a front-row seat to the death of the largest star we've ever found. Then it will be over, and the title of largest known star will pass to someone else. Another red supergiant sitting in another distant cluster, waiting for someone to point a telescope in the right direction and realize what they're looking at. But before we get there, before we start speculating about what might come next, we need to step back and ask a more fundamental question. Why do stars like Stephenson 218 exist at all? What is it about stellar physics that allows a ball of gas to swell to 2,000 times the size of the Sun without flying apart? Why do massive stars become red supergiants in the first place? And what does the evolutionary path from main sequence to hypergiant actually look like? Those are the questions we need to answer if we're going to understand what makes a star a monster. Human. Here is the data I collected on your response. Target, ~3030 words. Actual, 5,893 words. You overshot by 2,863 words, 94% over target. Please rewrite Chapter 5 to hit 3030 words. So Stephenson 218 sits at the top of the list. 2,149 solar radii, the largest confirmed star in the known universe. And if your first reaction to hearing that number is to ask how that's even possible, how a ball of gas can swell to a size that would swallow Saturn's orbit without simply flying apart into space, then congratulations, you're asking the right question. Because size alone doesn't tell you what makes a star a monster. The number is impressive, the scale is absurd, but the real story, the one that explains why objects like Stephenson 218 exist at all, is buried in the physics, in the life cycle of massive stars, in the nuclear reactions burning deep in their cores, in the balance between gravity trying to crush everything inward and radiation pressure fighting to blow everything apart. That balance, that constant war between collapse and explosion, is what determines whether a star lives quietly for billions of years or burns out in a few million, swells to monstrous proportions, and dies in a blast bright enough to outshine an entire galaxy. Let's start at the beginning. Not the beginning of the universe, the beginning of a star, specifically a massive star. The kind of star that has any chance of becoming a red supergiant or a hypergiant, because not all stars can do this. The Sun will never become a red supergiant. It doesn't have the mass. When the Sun exhausts the hydrogen in its core, about 5 billion years from now, it will swell into a red giant, not a supergiant, a giant. The outer layers will expand past Earth's orbit. The core will contract and heat up until it's hot enough to start fusing helium into carbon and oxygen. That phase will last a few 100 million years, then the helium will run out. The core will contract again, but this time it won't get hot enough to ignite carbon. The fusion will stop. The core will cool into a dense ball of carbon and oxygen, a white dwarf, and the outer layers will drift away as a planetary nebula. The Sun will die quietly, no supernova, no neutron star, no black hole, just a slow fade into darkness. That's the fate of every star below about 8 solar masses. They fuse hydrogen, they fuse helium, then they stop. They don't have enough mass to push the core temperature high enough to ignite the heavier elements. They plateau and cool, but cross that 8 solar mass threshold and everything changes. A star born with 8 times the Sun's mass or more has enough gravitational pull that when the core contracts, it doesn't just heat up a little, it heats up a lot, enough to ignite carbon, enough to ignite neon, enough to keep fusing heavier and heavier elements all the way up the periodic table until the core is made of iron. And that's where the music stops, because iron is the end of the line. Iron fusion doesn't release energy, it absorbs it. Every element lighter than iron, when you fuse it, gives off energy. Hydrogen into helium releases energy. Helium into carbon releases energy. Carbon into neon. Neon into oxygen. Oxygen into silicon. Silicon into iron. Every step releases energy, and that energy holds the star up. It creates an outward pressure that balances the inward crush of gravity. The star sits in equilibrium. Core pushes out, gravity pulls in, stalemate. But the moment you have an iron core, that stalemate ends. The core can't fuse anymore. The energy production stops. There's nothing left to hold the star up. Gravity wins. The core collapses. And when the core of a massive star collapses, it doesn't do it slowly. It happens in less than a second. The entire core, a ball of iron the size of Earth, weighing more than the Sun, collapses down to a sphere about 20 kilometers across. 20 kilometers. That's the size of a small city. The density becomes so extreme that protons and electrons are crushed together into neutrons. The collapse only stops when the core reaches nuclear density, the point where neutrons are packed so tightly they refuse to compress any further. The core rebounds. The outer layers of the star, still falling inward, slam into that rebounding core and bounce. The bounce sends a shockwave rippling outward through the star at a significant fraction of the speed of light. The shockwave blows the star apart. Everything outside the core, millions of solar masses of gas, gets ejected into space in a matter of hours. That's a supernova. The explosion releases more energy in a few seconds than the star produced during its entire lifetime. For a few weeks, the supernova outshines every other star in its galaxy. Then it fades. What's left behind is either a neutron star, if the core was light enough, or a black hole, if the core was too heavy to be supported even by neutron degeneracy pressure. That's the endpoint. That's where stars above 8 solar masses are heading. But the path from birth to explosion is not a straight line. It's a series of stages, each one shorter and more violent than the last. A massive star spends most of its life on the main sequence, fusing hydrogen into helium in its core. For a star like Stephenson 218, which probably started its life somewhere between 20 and 40 solar masses, that main sequence phase lasts a few million years. Compare that to the Sun, which will spend about 10 billion years on the main sequence. Massive stars burn hot and fast. The more massive a star is, the hotter its core gets, and the faster it fuses hydrogen. A star 10 times the mass of the Sun doesn't last 10 times as long. It lasts a tenth as long, maybe a hundredth. The relationship between mass and lifetime is not linear. It's inverse and steep. Double the mass and you cut the lifetime by more than half. Triple the mass and the lifetime drops by a factor of 10 or more. When the hydrogen in the core runs out, the core contracts. As it contracts, it heats up. The outer layers of the star, which still contain plenty of hydrogen, start fusing in a shell around the now dormant helium core. That shell fusion pumps enormous amounts of energy into the star's envelope. The envelope responds by expanding. The star swells. The surface area increases dramatically. The surface temperature drops because the outer layers are now much farther from the core. The star transitions from a hot blue supergiant to a cooler yellow or red supergiant. This is where the giants come from. The swelling, the cooling, the transformation from a compact, stable object into a bloated, unstable one. And the swelling doesn't stop when the star looks big. It keeps going as long as the shell fusion keeps dumping energy into the envelope. Some stars swell to hundreds of times their original size. Some swell to thousands. While the outer layers are expanding, the core is still contracting. Eventually, the core gets hot enough to start fusing helium into carbon and oxygen. That's the next stage. Helium fusion releases less energy than hydrogen fusion, so it doesn't last as long. A star that spent a few million years fusing hydrogen might spend only a few 100,000 years fusing helium. When the helium runs out, the core contracts again. If the star is massive enough, the core heats up enough to ignite carbon. Carbon fuses into neon and magnesium. That stage lasts maybe 10,000 years. Neon fuses into oxygen and magnesium, a few thousand years. Oxygen fuses into silicon and sulfur, a few years. Silicon fuses into iron, a few days. Each stage burns hotter, faster, and for a shorter time than the one before it. The star is racing toward collapse. And with each new stage, the core adds a new layer. Hydrogen burning in a shell around a helium core. Helium burning in a shell around a carbon-oxygen core. Carbon burning around a neon core. neon around oxygen, oxygen around silicon, silicon around iron. By the time the star is ready to explode, its core looks like an onion. Layers of different elements stacked on top of each other, each layer burning at a different temperature, each layer adding to the growing iron core at the center. When the iron core reaches about 1.4 solar masses, it can't support itself anymore. Collapse, supernova, game over. That's the script for every massive star. But not every massive star becomes a red supergiant. Some stay blue. Some turn yellow and then go back to blue. The path depends on the star's mass, its rotation, its composition, and how much mass it loses along the way. Mass loss is the wild card, and it's enormous. Red supergiants and hypergiants don't just sit quietly while they fuse heavier elements. They shed mass, constantly, in powerful stellar winds that blow material off the surface at speeds of tens of kilometers per second. The winds are driven by radiation pressure. The star is so luminous that the photons streaming outward from the core carry enough momentum to physically push gas away from the surface. For stars near the upper luminosity limit, radiation pressure is strong enough to overcome gravity. The outer layers don't need a supernova to get blown off. They're being stripped away in real time, year after year, shedding Earth masses of material into space. Stephenson 218 is losing mass right now. VY Canis Majoris is losing mass at a rate of about 30 Earth masses per year, 30 Earths every year. That's not sustainable. At that rate, the star is tearing itself apart. The outer envelope is so loosely bound that it's barely part of the star anymore. Every time the star pulsates, it kicks more material into space. Every time it has an outburst, it loses a chunk of its atmosphere. The nebulae you see around hypergiants like VY Canis Majoris, those glowing shells and arcs of gas, are the material the star has already lost, blown off in previous eruptions. Still glowing because it's being heated by ultraviolet radiation from the star. In another few thousand years, that material will cool, fade, and mix into the interstellar medium, and the star will have shed more. The process is relentless. Mass loss changes everything. A star that starts its life at 40 solar masses might lose half its mass or more before it explodes. That mass loss affects the star's luminosity, its temperature, its size, and its eventual fate. A star that loses a lot of mass might end up with a core light enough to produce a neutron star instead of a black hole. A star that loses less mass might collapse directly into a black hole without producing a visible supernova at all. The explosion you get depends on what's left when the core finally collapses. And what's left depends on how much the star shed along the way. Mass loss is also why some red supergiants turn back into blue supergiants before they explode. If the star loses enough of its hydrogen envelope, the deeper, hotter layers get exposed. The surface temperature goes up. The star's color shifts from red to yellow to blue. The star doesn't shrink. It just gets hotter on the outside, because the cooler outer layers have been stripped away. Astronomers call these objects Wolf-Rayet stars. They're the bare cores of what used to be red supergiants, stripped down to the helium and carbon layers, fusing heavy elements, racing toward collapse. They're small by supergiant standards, but they're incredibly hot and incredibly luminous, and they're on the verge of exploding. There's also a limit, a theoretical ceiling on how massive a star can be before it becomes unstable. The limit is fuzzy and depends on a lot of variables, but most models put it somewhere around 100 to 150 solar masses. Above that, the star releases so much energy through fusion that radiation pressure blows the outer layers away faster than gravity can pull them back. The star can't hold itself together. It either sheds mass until it drops below the limit, or it tears itself apart in a violent eruption that's not quite a supernova but close enough. Observationally, we found very few stars above 150 solar masses. They exist, or they did, but they're rare, and they don't last long. A star born at 150 solar masses might lose half its mass in the first million years of its life, blown off by radiation-driven winds so strong that they strip the star down to its core almost as fast as it forms. By the time the star is ready to explode, it might weigh only 60 or 70 solar masses, still massive, still heading for a supernova, but not the monster it started as. On the other end of the scale, there's a lower limit too. Below about 8/10 of a solar mass, the core never gets hot enough to ignite hydrogen fusion. The object contracts, heats up, but stops short of the temperature needed to start burning hydrogen. What you get instead is a brown dwarf, a failed star, an object that glows faintly from the heat of its contraction but never reaches the sustained fusion that defines a true star. Brown dwarfs are common. They're scattered throughout the galaxy, dim and hard to detect, sitting in the gap between the largest planets and the smallest stars. They're not monsters, they're barely stars at all. The monsters sit at the other end. The stars born with 10, 20, 50 times the sun's mass. The stars that burn so hot and so fast that they exhaust their fuel in a few million years and die in explosions that seed the galaxy with the heavy elements needed to build planets, atmospheres, and eventually life. Because that's the other part of this story, the reason massive stars matter. When a supernova explodes, it doesn't just destroy the star. It creates. The shockwave from the explosion is so hot and so energetic that it triggers nuclear reactions that can't happen inside a star. Reactions that build elements heavier than iron, gold, silver, platinum, uranium. Every atom of gold in every ring, every coin, every piece of jewelry ever made was forged in a supernova explosion. Every atom of iodine in your thyroid, every atom of calcium in your bones, every atom of iron in your blood came from a massive star that lived fast, died violently, and scattered its guts across space. You are made of star debris. The carbon in your cells, the oxygen in your lungs, the nitrogen in your DNA, all of it was built inside stars and released when those stars exploded. The sun didn't make those elements. The sun is too small. It took massive stars, stars like the ones we've been talking about, to build the periodic table, and it took supernovae to distribute it. So when you look at a star like Stephenson 218 and ask what makes it a monster, the answer is not just its size. The answer is its mass, its evolutionary path, its violent end. Stephenson 218 started as a massive star, burned through its hydrogen in a few million years, swelled into a red hypergiant as it fused heavier elements, and is now coasting toward the moment when its core collapses and it explodes. That explosion will briefly outshine the entire Milky Way. It will release more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. It will forge elements that don't exist anywhere else in nature, and it will scatter those elements across light years of space, seeding the next generation of stars and planets with the raw materials needed to build worlds. That's what makes it a monster, not the radius, the process, the physics, the fact that an object this large, this luminous, this unstable can exist at all. And here's the uncomfortable part. We don't fully understand the upper limits. Stephenson 218 is pumping out 440,000 times the sun's luminosity. That's nearly 10 times higher than the theoretical limit that was supposed to prevent stars from getting that bright. Either the models are wrong, or there's something about red hypergiants that allows them to bypass the limit. Maybe the mass loss acts as a safety valve, shedding material fast enough to keep the star from blowing apart. Maybe the star's low surface temperature changes the opacity of the atmosphere in a way that reduces radiation pressure. Maybe the star is rotating slowly enough that centrifugal forces don't add to the instability. We don't know. The models predict one thing. Observations show another. That gap is where the science lives. That's where the next generation of astronomers will spend their careers, trying to figure out how stars like Stephenson 218 manage to exist when the equations say they shouldn't. There's also the question of how many more are out there. Stephenson 218 is the largest confirmed star we've found. Confirmed is the key word. There are candidates. Objects that look like they might be even larger, but whose measurements are too uncertain to call definitive. Stars sitting in distant clusters, buried under layers of dust, too faint to study in detail with current instruments. Every time a new infrared survey goes online, a few more candidates show up. Some of them turn out to be smaller than expected once you correct for distance and extinction. Some turn out to be binary systems, where two stars are blending together and inflating the brightness estimate. But some are real, and some might be larger than Stephenson 218. We just don't know yet. The galaxy is big. The Milky Way contains somewhere between 200 and 400 billion stars. We've catalogued maybe a few billion of them in any detail. The rest are just dots. Faint, distant, unresolved. Any one of those dots could be a hypergiant. Any one could be larger than Stephenson 218. We won't know until we point a telescope at it, take a spectrum, measure the distance and run the numbers. That's the state of the field right now. We've found the largest star we've confirmed so far. We've measured it as carefully as current instruments allow. And we've learned that the universe can build objects far more extreme than we thought possible. Stephenson 218 is not an outlier, it's a data point. A single example of what happens when you take a massive star, let it evolve through every stage of fusion, and catch it in the final moments before it collapses. There are other data points waiting to be found. Other monsters sitting in distant star clusters, hidden behind dust, too dim to notice, waiting for someone to build a better telescope and look in the right place. And when those discoveries happen, when the next record holder gets confirmed, the process will repeat. The measurements will get refined, the models will get updated, the answer will shift. That's how this works. Science is not a list of facts carved in stone. It's a conversation. A slow, iterative process of guessing, checking, refining, and guessing again. The conversation about stellar giants has been running for decades. It's not over. And the next chapter is about to be written by instruments that haven't launched yet, surveys that haven't started, and astronomers who are still in graduate school learning how to run the analysis. The future of stellar discovery is sitting in telescopes under construction, in satellites being assembled, in proposals being drafted by teams who think they know where to look next. And that future is closer than you think. So we've traced the path. We started with the sun, that familiar ball of light sitting in the sky every morning, unremarkable in every way that matters until you actually stop and think about what it is. Then we stepped outward. Mu Cephei, Herschel's Garnet Star, a red supergiant so large it would swallow Mars if you dropped it into our solar system. Antares, the rival of Mars, bright enough to see with your naked eye but large enough to contain Earth's entire orbit. Canis Majoris, the former champion, the star that held the record for years until better measurements knocked it down a peg. Scuti, the star that took over the throne only to lose it when Gaia's distance data came in and the radius estimate shrank by half. And finally, Stephenson 218, the current record holder, sitting at 2,149 solar radii, a number so large it barely registers as real even when you write it out and stare at it. 2,149 times the radius of the Sun. A star so large that if you placed it where the Sun is, Saturn would be sitting at the edge of its photosphere. A star pumping out 440,000 times the Sun's luminosity. A star that's losing mass so fast it's tearing itself apart in real time. A star that exists in defiance of theoretical limits that say stars shouldn't be able to get that bright without blowing themselves to pieces. And sitting 19,000 light-years away, buried in a crowded star cluster, obscured by layers of interstellar dust, completely invisible to the naked eye, the largest confirmed star in the known universe, and most people have never heard of it. That's where we are right now. Stephenson 218 sits at the top of the list. The measurements are as good as we can get them with current instruments. The uncertainties are large, but even at the low end of the error bars, the star is bigger than anything else we've found. It's the ceiling, the upper limit, the biggest thing a star can be, except it's probably not, because the galaxy is enormous and we've barely scratched the surface. The Milky Way contains somewhere between 200 and 400 billion stars. The exact number depends on how you count, what you include, and which model you trust. But the ballpark figure is a few hundred billion. That's the total. The number of stars in our galaxy right now, burning away, scattered across a disk 100,000 light-years wide. Out of those few hundred billion, we've catalogued maybe a few billion in any detail. And by in detail, I mean we know their position, their brightness, and maybe their color. For most stars in the galaxy, that's all we have. A dot on a map, a magnitude measurement, a rough guess at the distance. We don't know their temperatures, we don't know their luminosities, we don't know their sizes. They're just there, faint, distant, unresolved. Any one of those dots could be a hypergiant. Any one could be larger than Stephenson 218. We won't know until someone points a telescope at it, takes a spectrum, measures the distance accurately and runs the numbers through a model. And that process, for a single star, can take years. The challenge is not that there aren't more giant stars out there. The challenge is finding them. Red supergiants and hypergiants are rare. Current estimates suggest there are only a few dozen hypergiants in the entire Milky Way. Maybe 100 if you stretch the definition. Compare that to the hundreds of billions of stars total, and you're looking at a needle in a haystack problem where the haystack is the size of a galaxy and the needle is dim, red, and hiding behind a cloud of dust. You can't just scan the sky and expect giant stars to jump out at you. Most of them are too faint. Most of them sit in regions of the galaxy where dust blocks visible light almost completely. You need infrared telescopes. You need surveys that cover the entire sky in multiple wavelengths. You need follow-up spectroscopy to confirm what you're looking at. And you need accurate distance measurements, which until recently were almost impossible to get for stars sitting thousands of light-years away in crowded fields. Gaia changed that. The European Space Agency's Gaia spacecraft launched in 2013 with one job: measure the positions and distances of more than 1 billion stars with unprecedented precision. Gaia used parallax, the apparent shift in a star's position as Earth moves around the Sun, to calculate distances. Parallax is an old technique. Astronomers have been using it since the 1800s, but Gaia took it to a level of precision that was unthinkable a generation ago. The spacecraft measured parallaxes down to milliarcseconds. That's 1,000th of an arcsecond. An arcsecond is 1/3600th of a degree. A milliarcsecond is 1,000 times smaller. To give you a sense of scale, A milliarcsecond is roughly the angle subtended by a coin on the Moon as seen from Earth. Gaia was measuring angles that small for stars thousands of light-years away. And it did it for 1 billion objects. When Gaia's data became available, astronomers went back and recalculated the properties of thousands of stars. Distance estimates that used to have uncertainties of 50% or more suddenly had uncertainties of 5%. Luminosity estimates that were based on rough guesses got replaced with real numbers. And size estimates, which depend on both distance and luminosity, shifted. Some stars got bigger. Some got smaller. Scuti got smaller. Canis Majoris got smaller. Stephenson 218 stayed large, but the error bars shrank. The whole field got more precise, and that precision revealed something uncomfortable. A lot of the old size estimates were wrong, not wildly wrong, not orders of magnitude off. Just wrong enough that stars that were supposed to be the biggest turned out to be only the second biggest or the third biggest. The rankings shifted, the record changed hands, and the new measurements left open the question of whether there are even larger stars waiting to be found. There probably are. Stephenson 218 sits in a star cluster that's only about 10 to 20 million years old. Young clusters like that are full of massive stars. Most of them are still on the main sequence, fusing hydrogen, burning blue and hot. A few have already evolved off the main sequence and swollen into red supergiants. Stephenson 218 is one of those. But it's not the only red supergiant in the cluster. There are others. Some of them might be larger. Some of them are probably too obscured by dust to measure accurately. The cluster sits 19,000 light-years away, right in the plane of the Milky Way, in one of the dustiest regions of the galaxy. The extinction is severe. Most of the visible light from the cluster gets absorbed before it reaches Earth. Infrared light makes it through, which is how we can study the cluster at all, but even infrared observations are tricky. The stars are crowded. The background is messy. Separating individual objects and measuring their properties accurately requires high-resolution imaging and careful photometry. It's time-consuming, it's expensive, and most of the stars in Stephenson 2 have not been studied in that level of detail. There could be larger stars sitting in that cluster right now, unnoticed, waiting for someone to take a closer look. And Stephenson 2 is just one cluster. There are thousands of young, massive clusters scattered across the Milky Way. Most of them are too distant or too obscured to have been surveyed in detail. Some of them sit on the far side of the galaxy, more than 50,000 light-years away, where the combination of distance and dust makes detailed observations almost impossible with current instruments. But those clusters exist. They contain massive stars. Some of those stars have already evolved into red supergiants, and statistically at least a few of them should be comparable in size to Stephenson 218 or larger. We just haven't found them yet. The tools for finding them are getting better. The James Webb Space Telescope launched in late 2021, and it has already changed the game for infrared astronomy. Webb's 6.5-meter mirror collects more light than any previous infrared telescope. Its instruments are sensitive to wavelengths that are completely blocked by Earth's atmosphere, which means it can see objects that ground-based telescopes can't detect, and it can resolve details in crowded fields that would be blurred together in lower-resolution images. Webb is not designed specifically to hunt for giant stars. Its primary mission is studying the early universe, exoplanet atmospheres, and star formation. But the capabilities it brings to the table are exactly what you need to find hidden hypergiants. Infrared sensitivity, high resolution, the ability to see through dust. If there are larger stars sitting in distant clusters, Webb has a shot at finding them. The next generation of ground-based telescopes will help too. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters across. 39 meters, that's the size of a small building. The ELT will collect more light than any telescope ever built. It will have adaptive optics systems that can correct for atmospheric distortion in real time, sharpening the images to the point where you can resolve details on the surfaces of nearby stars. And it will have infrared instruments that can take spectra of faint objects in crowded fields, the exact kind of observations you need to identify and characterize red supergiants sitting thousands of light-years away. The ELT is scheduled to see first light sometime in the late 2020s. When it comes online, the search for giant stars will take another leap forward. Fainter objects, more distant clusters, better distance measurements, more accurate size estimates. The list of known hypergiants will grow. The record for largest star will probably change hands again. But there's a limit. There has to be. At some point, you hit a ceiling where stars simply can't get any bigger without flying apart. The question is where that ceiling sits. Current models predict that stars can't exceed a certain luminosity, somewhere around 40,000 to 50,000 times the Sun's luminosity, before radiation pressure blows the outer layers away faster than gravity can pull them back. Above that limit, the star becomes unstable. It sheds mass in powerful winds. It pulsates violently. It might tear itself apart in an eruption that's not quite a supernova but close enough. Stephenson 218 is pumping out 440,000 solar luminosities. That's roughly 10 times the supposed limit, and it's not disintegrating. It's losing mass, sure, but it's holding together. Which means either the models are wrong, or there's something about red hypergiants that allows them to bypass the limit. Maybe the low surface temperature changes the opacity of the atmosphere in a way that reduces radiation pressure. Maybe the mass loss acts as a safety valve, shedding material just fast enough to keep the star from exploding. Maybe the star's slow rotation means there's no extra centrifugal force destabilizing the outer layers. We don't know. The physics is complicated, the models are full of assumptions, and the observations are sparse because there are so few hypergiants to study. There's also the possibility that we're looking in the wrong places. Most of the giant stars we've found sit in young clusters in the galactic plane. That makes sense. Young clusters are where massive stars are born. The galactic plane is where most of the star formation happens, but massive stars don't stay in clusters forever. Some of them get ejected. Gravitational interactions with other cluster members can kick a star out at high speed, sending it flying off into interstellar space. If a massive star gets ejected while it's still on the main sequence, it could spend the next few million years traveling hundreds or thousands of light-years away from its birthplace before it evolves into a red supergiant. By the time it swells to hypergiant size, it might be sitting far from any cluster, isolated in a region of the galaxy where nobody thinks to look for giant stars. Those runaway hypergiants would be even harder to find than the ones sitting in clusters. No crowding, no other bright stars to guide your search, just a single dim red object in the middle of nowhere, too faint to show up in most surveys, too far from anything else to be noticed. Some of them are probably out there right now, invisible, uncatalogued, larger than Stephenson 218, and we'll never find them unless we stumble across them by accident. Then there are the stranger objects, the ones that blur the line between star and not star. Brown dwarfs, for example. Brown dwarfs are objects that form like stars, collapsing out of gas clouds under their own gravity, but never get massive enough to ignite sustained hydrogen fusion in their cores. They're too small to be stars and too large to be planets. They sit in a kind of grey zone, The largest brown dwarfs can be nearly as massive as the smallest stars. The smallest brown dwarfs can be lighter than some of the largest planets. They glow faintly from the heat of their contraction, but they don't shine the way stars do. They're dim, they're cool, and they're hard to detect. More than 1,800 brown dwarfs have been identified so far, and that number is climbing every year as infrared surveys get better. Most of them were found in the solar neighborhood, within a few dozen light-years of Earth. But statistically, there should be millions of them scattered throughout the galaxy, maybe billions. They're just too faint to see at large distances. There are also planetary mass objects, worlds that formed the way planets do, by accreting material in a disk around a young star, but were then ejected from their star systems and now drift through interstellar space alone. These rogue planets are invisible in most surveys because they don't emit much light and they don't reflect light from a nearby star. But they exist. We've found a few of them. One example is CFBDSIR 2149, an object sitting somewhere between 4 and 7 times the mass of Jupiter, with a surface temperature around 700 Kelvin. It was found using imaging from the Canada-France-Hawaii telescope and follow-up spectroscopy from the Very Large Telescope. The object has no host star. It's just drifting, alone, dark, cold, barely glowing. The kind of thing you'd never notice unless you were specifically looking for it. And if objects like that exist, if the galaxy is full of rogue planets and isolated brown dwarfs and ejected planetary cores floating through the void, then the catalogue of objects we think we have is missing huge categories of things, not stars, not planets, something in between, something stranger. The point is, the universe is full of objects we haven't classified yet, objects that don't fit neatly into the boxes we've built. Objects that challenge our definitions of what a star is, what a planet is, what counts as large, what counts as massive, what counts as real. Every time we build a better telescope, we find more of them. Every time we push our instruments to their limits, we discover something sitting just past the edge of what we thought was possible. Stephenson 218 is the largest star we've confirmed, but confirmed is doing a lot of work in that sentence. It means we've measured it. It means the data is good enough to publish. It means other astronomers have looked at the numbers and agreed that yes, this object is what we say it is. But there are objects out there we haven't measured, objects we haven't noticed, objects sitting in the data from old surveys waiting for someone to go back and take a second look. Science doesn't move in straight lines. It doesn't proceed from discovery to discovery with clean transitions and obvious next steps. It stumbles, it backtracks, it finds something unexpected and spends a decade arguing about what it means. The story of giant stars is a perfect example. For years, Canis Majoris was the biggest. Then Scuti took over. Then the measurements got revised and Scuti shrank. Now Stephenson 218 holds the title. But that title is provisional. It's the best answer we have right now, based on the best data available, analyzed with the best models we've built. 10 years from now, the answer might be different. 20 years from now, it almost certainly will be. Not because the stars are changing, because we're getting better at measuring them, because our instruments are improving. Because someone will point a telescope at a dim red dot sitting in a distant cluster and realize what they're looking at. There's something humbling about that. The idea that the universe contains objects so large, so extreme, so far beyond anything in human experience, that we can measure them, calculate them, write papers about them, and still not really understand what they are. Stephenson 218 is a star. We know that. We know how it formed. We know what it's made of. We know how it will die. We've traced the entire life cycle from birth to supernova, but we don't fully understand why it's as large as it is. We don't know why it hasn't torn itself apart. We don't know if there's an upper limit to stellar size or if stars can just keep swelling until something else intervenes. The models give us predictions. The observations give us data, and sometimes the two don't match. That gap, that space between what we think should happen and what actually happens, is where the interesting questions live. It's where the next generation of astronomers will spend their careers trying to close the gap, trying to build better models, trying to explain why the universe keeps producing objects that shouldn't exist according to the rules we thought we understood. And here's the thing. We're not done. The search for giant stars is not over. It's just starting. Gaia gave us distances. Webb is giving us infrared imaging. The ELT will give us high-resolution spectroscopy. Each new tool opens a new window. Each new window reveals objects we couldn't see before. The galaxy is large. We've surveyed maybe 1% of it in the kind of detail needed to find and characterize hypergiants. The other 99% is still out there, waiting, full of stars we haven't catalogued, clusters we haven't surveyed, objects we haven't noticed. Some of those objects are probably larger than Stephenson 218. Some of them are probably stranger. Some of them are sitting in regions of the galaxy we can't observe yet because our instruments aren't good enough. But they will be. In 10 years, in 20, in 50, the telescopes will get bigger, the detectors will get more sensitive, the surveys will get deeper. And every time we push the limits a little further, we'll find something new. That's the trajectory, not a straight line to a final answer, a slow, iterative crawl toward better and better approximations of the truth. The largest star we've found is Stephenson 218. The largest star we'll ever find is still out there, somewhere, burning away in a distant corner of the Milky Way, too faint to see, too far to measure, too obscured to notice, until someone builds the right telescope and looks in the right place. And when that happens, when the next record holder gets confirmed, the process will repeat. The measurements will get refined, the models will get updated, the answer will shift, and we'll be reminded once again that the universe is larger, stranger, and more extreme than we have the capacity to imagine. Stephenson 218 is not the end of the story. It's a chapter, a single data point in a much larger investigation, a snapshot of where we are right now in our understanding of stellar extremes. And where we are right now is standing at the edge of a cliff, looking out over a landscape so vast that we can barely see the horizon. The sun sits behind us, familiar and small. In front of us, scattered across the galaxy, are monsters. Objects so large they swallow planets. Objects so bright they outshine entire star clusters. Objects so violent they tear themselves apart in real time. And we're just beginning to find them. The search continues. The instruments improve. The data accumulates. And slowly, piece by piece, observation by observation, we map the extremes. Not because we need to. Not because it changes anything about our daily lives, but because we're curious, because we want to know, because there's something fundamentally human about looking up at the sky and asking how big, how far, how strange can it get. Stephenson 218 is 2,149 times the radius of the Sun. That's the answer right now. It won't be the answer forever, and that's exactly how it should be. You walk outside tomorrow morning, and the sun will be there. Same as it was yesterday, same as it will be a year from now. Unremarkable, predictable. A dot in the sky you've seen 10,000 times and stopped noticing 9,999 times ago, and now you know what you're actually looking at. Not just the sun, the baseline. The unit of measurement against which every monster in the galaxy gets compared. Stephenson 218 sits 19,000 light-years away, pumping out 440,000 times the Sun's luminosity, swollen to 2,149 times its radius, holding together in defiance of every limit we thought existed. The largest confirmed star in the known universe. A title that will probably change hands again in 10 years when someone points a better telescope at a distant cluster and finds something even larger sitting in the data, because the galaxy is enormous and we have barely started looking. That's the uncomfortable truth. We don't know where the ceiling is. We don't know if there even is one. The models predict a limit. The observations keep finding objects that exceed it, and the gap between what should be possible and what actually exists is where the most interesting questions live. Stephenson 218 is not the answer, it's a clue. A single data point in a field so large we've mapped maybe 1% of it. The rest is still out there, waiting. Full of stars we haven't catalogued, clusters we haven't surveyed, objects so extreme they'll force us to rewrite the textbooks when we finally notice them. The search continues, the instruments improve, the universe, indifferent to whether we understand it or not, keeps producing monsters. And we keep looking up. Because that's what we do. We measure the immeasurable. We name the unnameable. We find the edge, and then we